Assalamualaikum and a very good morning to Mr. Engineer Solhin Asad, MT, Dean of Faculty of Engineering Sebelas Maret University, Dr. Nikan Suryan Mary, STMC, Head of Civil Engineering Program Faculty of Engineering Sebelas Maret University, Professor Stefanus Adi Setiawan, ST, PhD from Sebelas Maret University, Mr. Iwan Supriyanto, ST, from PT Gria Indah Prakasa, Professor Dr. Abdurrahman bin Mohsen from University Teknology Malaysia, Raihan Rizal Herdiansyah, Head Committee of Civilweek 2021, Faza Bagus Fauzan, Head Committee of International Fabric Competition, Civilweek 2021.
Distinguished finalists, faculty, ladies and gentlemen, salam sejahtera and hello from Indonesia. My name is Stephen Samuel.
And I'm Nivita Putri Maharani.
And we are absolutely honored to be your MC today. We would like to give the warmest welcome to the final round of International Concrete Competition, Civilweek 2021. In today's final round, you are going to present your ideas and innovations to the juries. We wish very good luck for you who have a presentation scheduled today, and also for you who has a presentation scheduled tomorrow.
Before we start the final round, we have an opening speech from the Dean of Faculty of Engineering Sebelas Maret University. Ladies and gentlemen, please welcome Mr. Solhin Asad.
Okay, thank you, Mbak Dita. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi ya. Very good morning. The Honorable Head of Department of Engineering, Ibu Dr. Niken Suryan, the Honorable Judges of the International Concrete Competition, Bapak Iwan Supriyanto, Pak Profesor Abdurrahman bin Muhammad Sam from Institut Malaysia, and Pak Profesor Stefanus Adi Setiawan from Sebelas Maret, all the finalists, participants, and the committee. My name is Solhin Asad. I'm currently the Dean of Faculty of Engineering at Sebelas Maret. In this occasion, I would like to welcome you all to this International Concrete Competition 2021 in the final round or final judging. This International Concrete Competition is organized or is a part of the Civilweek 2021, organized by Civil Engineering Students Association of Universitas Sebelas Maret. As a Dean, I would like to extend my congratulations to all the finalists, 10 finalists today. Those are from 10 teams, who already selected by the judges. Those are 4 from abroad, from Malaysia, from Singapore, and from Thailand, and other 6 finalists from Indonesia. Ladies and gentlemen, this competition is intended for the civil engineering student to learn and to implement the current advancement of concrete technology with the relevant the issue that we are facing currently, environmental issue and in advancement of concrete technology. Currently, there is a high demand of the concrete as a construction material. However, at the same time, we are facing also the challenge in our degradation, our environments. And we have to explore our construction material from the nature, but we have to explore it wisely and carefully. Yeah, that's why with the advancement of concrete technology, inshallah, we may overcome all of those our problems. At the same time, we may develop our infrastructure and we may develop our construction safely. Yeah. This competition is, inshallah, will enhance the students' understanding in sustainability issue related to the advancement of concrete application in construction. Ladies and gentlemen, my deep appreciation to the committee, to the students who initiate this competition. Thank you for all your great effort and to organize this competition efficiently. With the theme of the sustainability, high early strength concrete for quick use in construction. Ladies and gentlemen, I would like also to extend my sincere gratitude to all the judges. One to Bapak Insinyur Iwan Suprianto from PT Indah Gria Prakarsa, and the second to Bapak Profesor Abdul Rahman bin Abdul Sam, bin Muhammad Sam from University Teknologi Malaysia, and the third to Profesor Bapak Profesor Stefanus Adi Kristiawan Universitas Sebelas Maret, who already spend their time, valuable time, and they spend a lot of effort to this competition. Thank you for all sponsor. Lastly, I wish you have a wonderful and exciting experience during this final judging session. Good luck to all the finalists. Thank you very much. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Mr. Sohin Asad, for the opening speech and for the wishes. Next, we're going to have an opening speech delivered by our Head of Civil Engineering Study Program, Faculty of Engineering, Sebelas Maret University, Mrs. Niken Silver. Ladies and gentlemen, please welcome Mrs. Niken.
Sorry, there's a technical mistakes from Unican's opening speech. Now we're going to have an opening speech from our head committee of Civilweek 2021, Raihan Rifil Herdiansyah. For Raihan Rifil Herdiansyah, the time and screen is yours.
Good morning, honorable quizzes, dear colleagues and respectable finalists. Thank you to each and everyone you of for being here with us today. I'm very pleased to be able to welcome you all to the final round of the International Concrete Competition Civilweek 2021. Today is the first of the final round, and the finalists and the committee have come through so much to be at this point, and let me express my most sincere respect to all of you. I would also like to express my deep gratitude towards our generous sponsor and members of the engineering faculty of Universitas Sebelas Maret, without whom it would not be possible for us to make it this far. In today's final round opening ceremony, I, as the head committee of Civilweek 2021, would like to focus on the finalists that are going to compete. You have all been selected for the final round because of the ideas and innovation that you have poured into your work. Your passion of civil engineering has made your team and the university you are representing to be able to take place in the International Concrete Competition final round. For me, it is a wonderful achievement of itself, and I, on behalf of all Civilweek 2021 committee, am proud to have you all here. In this final round, you will present your work and share your ideas and innovation to all of us. I really hope that the experience and knowledge will be beneficial to all of us and help us develop ourselves. Without taking much more time, I wish you all very good luck and may your endeavor bring you the best. Thank you.
Thank you very much, Raihan Rifil Herdiansyah. And now we have an opening speech delivered by our head of Civil Engineering Study Program, Faculty of Engineering, Sebelas Maret University, Mrs. Niken Silmi.
Distinguished finalists and Civilweek Committee, my name is Ms. Niken Silmi Surjandari, and I'm the head of the Department of Civil Engineering at Universitas Sebelas Maret, Surakarta. It is my pleasure to warmly welcome all of the finalists to the International Concrete Competition Civilweek 2021. First of all, I would like to congratulate all of the finalists in this year's International Concrete Competition. It is without a doubt an astonishing achievement, especially in this condition where we have to limit our activities due to the COVID-19 pandemic. And for my beloved Civilweek Committee, I'm really proud of you all. Even with the obstacle from the pandemic, you are still able to organize such a great event. As the head of the Department of Civil Engineering at Universitas Sebelas Maret, it is a must for me to always support all of the innovative and positive events that students hold. Because of that, I really hope that the International Concrete Competition can be a platform for all of the participants to gain more knowledge and the experience in the concrete engineering field. And in the end, I would like to say good luck to all of the finalists. I believe you can give the best for today's final. Also for the committee, I hope that this year's international concrete competition will go smoothly without any meaningful obstacles. Thank you. Good afternoon.
Thank you very much, Mrs. Niken Selmi Suryandari, for the opening speech and the prayer. We would like to mention our general sponsor, PT Adikarya Persero Tbk, PT Hutama Karya Persero, PT Waskita Karya, PT Jaya Konstruksi Manggala Pratama Tbk, PT Wijaya Karya Rekayasa Konstruksi, PT Jogja Solo Marga Makmur, Kadang Koding Indonesia, PT Prima Unggul Persada, PT Mandem Indonesia Tbk, PT Berantas Abipraya, and Bank Negara Indonesia, and also our media partner, Radio Solo Post FM. In this room, we already have our 5 finalists. The first finalist is Aeropile Drive. The second finalist is Bakul Beton S62. The third finalist is Semar Adhideva. The fourth finalist is Ragex. And the fifth finalist is Abidin Ganesha.
And the 3 juries, Professor Dr. Abdul Rahman bin Marsam from University Teknology Malaysia, Mr. Iwan Supriyanto ST from PT Kriya Indah Prakasa, and Professor Stefanus Adi Kristiawan ST PhD from Sebelas Maret University. For the other teams who have no presentation scheduled today, we kindly ask you to leave the room.
Hello. Okay, we will set up the slides now. Okay.
Okay, for the team who will present first is Aeropile Drive team from National University of Singapore. Its members consist, without further ado, for the Aeropile Drive team, the screen is yours.
Okay, thank you so much. Good morning, everyone. My name is Sean and my partner is John. Together, we are Aeropile drivers from the National University of Singapore, NUS. We are very grateful for this opportunity to be in top 10, to be given this chance to go through our innovation, low carbon concrete with high early age strength. So before we get into the meat of the presentation, we would like to go through our presentation outline first. So for the background, we'll briefly discuss how we came up with our innovation or how we chose our innovation. For the methods, we will run through how we get our materials and what we do for casting. Discussion is running through the results and the analysis, and then we will go through the conclusion and the suggestion for our project. So some background. With the rising effect of global warming, civil engineers are at the forefront of climate change mitigation. 5 to 8% of man-made CO2 emissions are from the production of cement. And also with the recent pandemic, there has been a need for rapid infrastructure development, a need for quick medical facilities to be constructed. So these are the challenges. There is an urgent need to reduce cement, but by using less cement, it will lead to a lower concrete strength. For rapid industrial developments, that we need high early strength in order for rapid construction. So some considerations. The most realistic and proven approach to reduce cement content is to use supplementary cementous materials like SCM, like fly ash and GGBS. However, early age strength is not easily achieved if cement is largely replaced by SCM. We also can use high temperature for curing, which would increase the early age strength, but this would further increase the energy consumption, making it less sustainable. We can also use special admixtures like accelerators in order to achieve this early strength, but this will result in a poor long-term strength. So we came out of our innovation, limestone calcined clay, Lc3 cement. We proposed a novel type of supplementary cementous materials, LCM, to produce low carbon and good early age strength concrete. The two main components of Lc3 cement is calcined marine clay and limestone. So briefly about our materials, clay is typically found in tropical and subtropical environments, which are indicated by the yellow and pale green regions on the global map you see on the right. But we'll be mainly focusing on marine clay. Marine clay is widely distributed in coastal regions like in Southeast Asia, like Singapore, Malaysia, Indonesia, and Thailand. It has weak soil properties and cannot be used for construction or foundation material. Hence, it is a waste material. It is typically sent offshore site for removal. And in 2011, 8.5 million cubic meters of excavated materials were generated in Singapore. Okay, so when we get our marine clay, we boil it and we calcine it at 700 degrees Celsius. Our marine clay has a colonite content of 37%. Marine clay undergoes chemical change at 700 degrees Celsius, becoming more reactive and thus able to replace cement. And we source our marine clay from a local construction site in wet form. The second component of Lc3 cement is limestone powder, which is a widely available material. Okay, so what are the advantages of using this Lc3 cement? The first advantage would be the strength. So it has good early strength, as fine clay particles are able to react faster than other SCMs. It also has comparable long-term strength, as you can see in this graph. The mechanical properties of concrete with Lc3 cement are comparable to those of reference pure cement mix from 7 days onwards. Okay, the second advantage of Lc3 cement, sustainability. The calcination temperatures are lower than cement clinker production, hence calcination processes use less energy. There's also the use of expensive and complex materials are not needed in this production, and it does not require special or high temperature curing or mixing, which would help increase our production capacity and sustainability. Replacing a portion of cement to limestone and calcined marine clay powder would help to reduce our carbon footprint. Through this use of Lc3, we are able to recycle this waste into a useful product, forming a circular economy. This would reduce environmental issues like pollution, loss of flora and fauna due to excessive dumping of waste and global warming. In addition to that, we would also be able to save on material costs, free up money that can be spent on social causes, and boost resilience to supply shortage. So before we move on to the methods, we would like to mention the article that inspired our idea for the Lc3 cement. So this article features an NUS research on marine clay, the first project in the world to use marine clay that is able to reduce embodied carbon by 50% in concrete. Okay, so for our method of preparation for calcined marine clay. So when we get our marine clay, we first air dry it for 1 week, and then we oven dry it at 100 degrees Celsius for 24 hours. Proceeding that, we break the large chunks into smaller pieces with the jaw crusher, and then we ball mill the clay into a medium size of 5.5 micrometers. This is to ensure the fineness of the particles and improve the reactivity. After we get this powder, we calcine it at 700 degrees Celsius for 30 minutes. With that, I'll pass my time on to John, who will go through the rest of the slides.
Thank you, Sean. And I'm John, and right now I'll be presenting on the mix design. So the following table shows our mix design for 1 meter cube of concrete. So the mix proportion for our high strength concrete was designed according to ACI 211.4 standard. And in our report, we had a total of 9 steps of how we got our mix design. But on this slide, I will just highlight some key points on our mix design. So for the cementitious materials, they consist of OPC, calcined clay, and limestone. So we use a low water to cementitious materials ratio of 0.3. So we chose this ratio so as to achieve our desired strength. So in theory, we require 480 kg per meter cube of OPC cement, but because of the replacement effect of this calcined clay and limestone, we only require a cement content of 280 kg per meter cube. So bearing in mind that the maximum allowed is 300 kg per meter cube. In addition, we use a calcined clay to limestone ratio of 2:1. And on to our method of casting of concrete. So firstly, the dry ingredients were added into the mixer, starting with the coarse aggregate, fine aggregate, calcined clay, limestone, OPC cement, and the dry mixing was started for 3 minutes. After which, we added water and super plastic sizer into the mixer, and the mixing was started for 8 minutes. So once the mixing was completed, we fill up the mold on a vibrating table, and then we did the 1-day curing at room temperature, covered with a plastic sheet. And on to our discussion for our results. For the slump results, we got a good slump value of 80 mm. And according to EN 206, the fresh concrete can be classified as class S2. So for our strength, at the beginning, we predicted a 1-day strength of 25 MPa and a 28-day strength of 80 MPa. So the 1-day strength is predicted from results of trial mixes conducted just before the competition casting. And the 28-day strength is predicted from a research study done by Du and Pang, where they also utilize Lc3 cement. So for our actual 1-day strength, so on the following table, it shows the specimens and the strength that we got. So for all 3 specimens, they had a strength that was relatively close. They gave us the average strength of 24 MPa. So the average strength of 24 MPa meets the minimum requirement strength of 15 MPa. And our actual strength of 24 MPa is very close to what we have earlier predicted of a 25 MPa. And next, for the discussion of our life cycle cost analysis. So the following table shows the life cycle cost analysis of our concrete mix. So it shows the amount needed, the cost, the energy requirement, and the carbon emissions. So the raw materials of our concrete, namely the cement, sand, and aggregates, they are transported from Malaysia, which is Singapore's closest neighbor. And the costs are estimated from UN Comtrade database 2020. So both marine clay and limestone, they are low cost material because the marine clay is a waste product and limestone is a widely available material. So sorry, go back. So the calcined clay costs $2 USD because energy is required to crush and calcine the clay. Yeah, next, please. Okay, so for our second part of our life cycle cost analysis, we did a comparison between our proposed mix and the pure cement reference mix. So we can tell from both that our proposed mix is cheaper and it consumes less electricity, and also it has a lower carbon dioxide, carbon monoxide, and sulfur dioxide being produced. So all in all, the use of our Lc3 cement is able to give cost savings, reduce energy requirement, and carbon emissions. So hence there is this potential industrial scalability. And lastly, to conclude, Lc3 cement is a sustainable concrete that has a low embodied carbon and also has a low cement content of 280 kg per meter cube. And from our results, it has shown that Lc3 cement is able to give high early strength of 24 MPa. And furthermore, Lc3 cement is able to address the increasing solid waste disposal problems in developing countries by employing and recycling this locally produced waste. So we have the four following suggestions. Firstly, as with all new materials, further studies can look into the long-term durability performance of Lc3 concrete in terms of its water absorption, shrinkage, and chloride resistance. Further studies can also look into producing sustainable mortar comprising of the local waste marine clay, and also further studies look into optimum design mix of Lc3 cementitious material and the consistency of the fresh concrete. And with that, we come to the end of our presentation. We thank you so much for your kind attention.
Okay, thank you very much for Aeropile Drive team. We will enter the interview session. For the juries, for question and answer session, there will be 10 minutes for every jury. For the first, Mr. Professor Dr. Abdul Rahman bin Mosam. Do you have any question?
Okay. Thank you. Very good morning. Can you hear my voice?
Yes, yes, sir.
Okay, all right. So thank you very much. Group but Aeropile drivers. Very nice name for the group. Okay. How you come up with the group group name?
Oh, because we like piling, so we just we didn't have any much thought for this naming. Yeah, because Aeropile is a machine.
Yeah. Okay, all right. Okay, thank you for that. Okay, so your concrete is low carbon concrete with high early strength. Yeah.
Yep.
Okay, and then you use supplementary material, clay and limestone.
Yes.
Clay and limestone. Okay, and then you have give the reasoning why you use clay and why you use limestone. Yes, I'm wondering how much the waste in terms of the amount, because our term nowadays is sustainable. If let's say once you use it and then finish and then there's no more left. Okay, so it is not sustainable. Sustainable means continuous, continuous supply of this waste, clay, and also limestone. And so, do you have any idea how much that's available?
Yes. I think from our research is that sorry.
Yeah,
okay, so there's about 8.5 million cubic tons of excavated materials, not specifically marine clay, but I think there's quite a lot of marine clay waste in the Southeast Asia region.
So it become a waste material,
Yeah.
So marine clay and inland clay, for example, is it two different things or?
So I think marine clay is specifically in Southeast Asia. Then when we look at like overseas, like in the UK and all that, their clay has slightly different properties compared to marine clay. So I think one of the things that like we kind of like researched and found out was like the coulonite content would change in different types of clay. So for ours is 37%. Yeah.
Okay.
Yeah, I think I'm going to add something. Thank you for your question. I think that was very good. Can go back to slide 6.
Yeah.
Okay, so I think the concern of what if there's no more, what if our clay runs out? Yes, in our local region here, we have mostly marine clay, but actually for Lc3, we can also use any type of clay that does not have to be marine clay. So as long as it's a clay material, so we can use, and clay is in abundance around the world. So as you can see in this photo, in the yellow regions and in the pale green regions. So one thing that differs between our marine clay and clay is the pozzolanic properties. So like what Sean said, it has a different coulonite content, and because it has different coulonite content, the calcination temperature would also differ. But all in all, there's an abundance of clay that can be found worldwide. And also marine clay is a waste product. So yeah, this is an innovation to recycle this waste. Yeah.
Okay, all right, thank you. So
Yeah,
in
thank
terms
you.
of sustainability, meaning to say that we need to use whatever the waste, it is not the clay. Clay is, yes, we have natural resources of clay that we make to produce cement, isn't it? If let's say we produce more and more cement, so we have to use more and more clay. That is natural resources.
Oh,
So
yeah.
that will affect the environment. Am I right?
Yeah.
So, but if let's say it is a waste, then we reuse the waste, and that is related to sustainability lah. Because when we talk about sustainability, we try to use less natural resources. Okay, and then you use like clay and limestone. Why you combine clay and limestone?
Because when we replace cement, we need the limestone because most part of cement is made out of limestone. So we need some properties of the limestone.
Yes, cement contain limestone contain calcium oxide.
Yes.
Again, limestone is natural resources, isn't it?
Yes, but they are all widely available materials. Clay and
at the moment, natural resources is widely available. But if let's say we use natural resources, because I want to relate to in terms of sustainability, and then at the same time we try to preserve, to take care of our environment, isn't it?
Yeah.
Yes.
So that is the whole idea nowadays is in terms of how to minimize the use of natural resources. Natural resources mean it is not the waste. So we try to use as much as possible the waste that can be used in our construction.
Yes.
Actually, I would like to answer the question that you asked just now about marine clay being a resource. I think yes, clay is used in cement production, but we need to remember that cement production uses a lot of energy compared to calcination. So this would mean that like even though we still use the material of clay, the amount of energy used is different. So it's a lot more sustainable than producing more cement. Yeah, and most of our marine clay, most of the marine clay is actually sent into for dumping and excessive site for removal. They are not used for production of cement, therefore they cannot be considered materials that resources that would have been used for cement if they are used for dumping. Sorry,
okay lah. So we need to separate between natural resources and also waste material.
Yeah, it's a waste material.
The production of cement is our aim is to reduce the CO2, isn't it?
Yes.
The release of CO2. Okay, all right. Okay. One more thing. You target the early strength is 25, isn't it?
Yes, we can go
Okay.
to that slide.
So I would say the theme of this competition is sustainability, high strength concrete, quick application, isn't it? More or less
Yes.
sustainability, high strength concrete, quick application. Okay. Do you think that the high early strength, is not high strength? Do you think that the use of higher strength, because your target 28 days is about what 80, 80?
Sorry, the 28 day strength.
Your target 28 days strength is what 80 megapascal, isn't it?
Yes,
Yeah.
correct. 88.
Okay, all right. So in terms of the application in construction, you said that we want to construct as early as quick as possible construction. Is it in terms of the grade of the concrete? Grade 25, and let's say strength 25 is grade what we call it, a normal grade concrete. Grade 80 is high strength concrete. So in terms of application, is it practical that so we need, because we have a high early strength, and then at the end of the day the strength of the concrete is grade 80, and then you want to construct just a 2 or 3 story building. What is your comment? High early strength is okay, but in terms of high strength,
Okay. Or like the high is it the high strength is not good or?
Okay, it's no problem. Because when you have a high early strength, let's say 25, so the latest strength probably can get for high strength, because your water cement ratio is 0.3.
Yes.
So what is your comment on that? For application,
Are you asking because of the water content 0.3?
No. Why you target for high strength concrete?
What's our target? In the long term for our design?
Yeah. 28 days.
We use a high strength concrete mix so as to get the early strength, and also so because of this early strength, it also leads to a high strength in the 28 days.
Yeah, definitely lah. Okay.
Yeah.
All right. So meaning to say that this is for high-rise building. For high-rise building, for example. But it's for normal construction. So if let's say we target nowadays, if let's say relate to the construction, so normal construction, 2-3 stories high building, isn't it? Yeah. Something like that. It's okay, right?
Yeah, but our focus was more on the 1 day strength.
1 day strength.
Yes.
Okay.
So because
the concept is the sustainability, high early strength, quick construction. Yeah, that is the theme, isn't it?
Yeah. So like the good strength in the 28 days was a bonus.
It's a bonus.
Yeah.
All right. Okay. All right. Okay. So you use cement strength class is 52.5, is it?
Yes.
It's not just 42.5 or ordinary Portland cement. You use repeat hardening Portland cement, isn't it?
No, we use cement 1.
Yeah. So that really 52.5 is related to repeat hardening Portland cement.
Oh, really?
That is for the rapid hardening. Rapid hardening means the early strength, to gain the early strength faster, quick. That's why it's 52.5, isn't it? Strength class.
No, actually 52.5. I thought it's ordinary. It's cement 1.
We have 52.5. We have 42.5. And then 32.5, isn't it?
I'm sorry, sir. Your time is up.
Okay, all right. Just one just to finish up. So meaning to say that between the cement and the clay and limestone that you use, which one that contribute to the early strength?
Sean, can go back to the previous slide. somehow.
You have OPC.
Yeah, it was
OPC.
actually the calcine clay, back somehow.
Mm.
The one show the high reactivity.
High reactivity. Slide, do you know the slide number?
At least after 10. Somehow. No, after 10, can 7, I think 7. Yeah, this.
Okay.
Okay, so like the marine clay becomes a reactive, so it's able to replace cement. So it becomes a cementitious. So that contributed mainly to the strength.
Okay. All right. Okay. All right. So thank you very much. Thank you. And then I will leave to the.
Okay, thank you, Professor.
Yeah.
Next, the second is Mr. Iwan Supriyanto. Do you have any questions?
Okay, thank you. I have some question for Aeropile driver, yeah. You use two material, which is a calcined marine clay and limestone. How do you know the both material can be used as supplementary cementing material? How do you know? Can you explain?
Yes. Thank you for your question. Because there was previous research, literature review that was they also make use of this limestone calcine clay. So where they use limestone powder and clay to kaolinite clay to replace cement. So for us, we took that approach, but we instead of using normal clay, we use a waste material, which is marine clay. So because even as in Singapore, as the underground activities become more and more, there is this issue of more waste excavated material. So that was the approach that we took it. So we use limestone and thus marine clay.
Yeah. What is the chemical content of this both material?
Of this both.
Yeah, the chemical properties of these two material.
Okay, so for the marine clay, it has we did a thermogravimetric analysis to find the kaolinite content, and we found it to be 37%.
What is? Sorry, silica?
No, for the marine clay, we did the TGA, which is the gravimetric analysis, so as to find the kaolinite content.
How they react in concrete? Can you explain? What is the chemical reaction mechanism of these two material in concrete, so they can contribute in your L strength as supplementary cementing material?
Sorry, give us a minute. I think what you're asking for is the chemical properties within the marine clay, right? Like what is the silica, alum or something like that? Like
yes,
that content, right? Okay, give me a minute. We need to check through some of the notes, some of our literature review. Okay, so marine clay has iron, silica, has potassium, has alum, but you're asking what is the major contributor, right, for the strength?
Yeah. How these two material contribute in your L strength? What is the chemical reaction of these two with other material in concrete?
Right. Okay. I think
how they react.
Wait, give me a second.
Have you done the other testing to to make sure that these two material is classified as cementing material, such as maybe you have the data of pozzolanic reactivity of these two?
Actually, we did not did any chemical testing on these two materials, but we thank you for this suggestion. We will add it in our future research. But one thing we know for sure is what we did was we did a reference pure mix, and then we added and then we substituted cement with these two materials, and we are able to give a relatively good strength as compared to the reference pure mix. And so we were able to find out that there was a cementitious material properties. Like, we do not know the exact chemical, but based from our results, it has shown that there is cementitious properties.
So if you don't know the chemical properties of these two, how you make sure that these two material is classified or contribute in your Li strength? What is the most chemical content of these two? Calcium oxide or silicon dioxide?
It is.
So you can know how they react and contribute in your strength.
Yeah, I understand the question.
Your Li strength is quite high. But
Yes.
your one day strength. Yeah? So I want to know what is the most factor contributing in your one day strength? These two SCM or because of other factor?
Is the reaction after it's calcined, but we can't sorry, Rina.
In this slide, marine clay undergoes chemical change at 700 degrees Celsius, becoming more reactive.
Yeah.
Yeah. Can you explain the chemical change? What is the chemical change happen in after 700 degrees Celsius? Becoming more reactive.
Yeah.
Okay, because
why you said that it's becoming more reactive?
Sean, can you go to the advantage?
Yeah.
Advantages, like
this one or sustainability?
Sustainability. Back.
Strength.
Yeah. Okay. So based on the literature review by Lc3 Cement and etc. So this actually fine clay particles, they are able to react faster than other type of SCM because of their fineness. Because we grind them until very small. So they're able to react faster than other types of SCM like fly ash and GGBS.
Okay.
So as a result, it's able to give us the good early strength. So, but in terms of the chemical properties specific, we do not. Sorry.
More react is about the what is the particle size after burning or after
5.5 micron meter.
We have the distribution.
This one.
Yeah.
Is it more finer than cement? The clay, the calcium clay?
Yes.
Okay. Can you go back to the slump?
Yeah.
Yours this 80 mm slump after edit the hyperplasticizer?
Yeah, with the SP,
Of the
super
DFP.
plasticizer.
What do you mean? 8
Uh,
cm slump can be applicable in the actual condition or not? With this type of slump.
Sorry, can you repeat the question again?
Because your slump I think is quite low, yeah, to apply for actual condition application. Why don't you try to make a flowable concrete, something like that?
Okay, our focus here was a high strength concrete because we wanted the high early strength.
Yeah.
Yeah. So as a result,
so that's why
we had a very low strength.
Your strength result is because of your very low water cement ratio, or because of these two supplementary cementing material?
No, it was because of a very a low water to a cementitious ratio, materials ratio. We use a 0.3. Usually a normal mix will be a 0.6. Yeah, we use a very low one, 0.3, so as to give us the high strength.
Okay.
Sorry, Mr. Iwan, your time is up.
Is enough? Okay.
Okay, thank you very much, Mr. Iwan. Last Yuri, you have 10 minutes. Please, Professor Stefanus Adi Kristiawan, do you have any question?
I'm sorry, I think you're muted.
Okay, good morning.
Good morning.
Thank you for the time for me to discuss with this team. I think you have a very good presentation, very clear what you want to do with your concrete and how you achieve your goal. Okay, at least high early strength already achieved. Yeah, your target is very high, 25, and you got 24. And I don't know whether the 28 days also achieve 80 megapascal or not yet.
No, we didn't test for that.
Yeah,
Okay.
We have not tested yet.
Okay. So you also try to use calcium clay and combine with the limestone to make sustainable cementitious material. If we consider the sustainability aspect, then we may also consider, as the first judges said, that we do not only quantifying the waste product, also emission, the consumption of electricity, energy, and so on, but also considering whether we use natural resources or we use some waste material. Yeah, since in your material you still using natural resources, yeah, marine clay and also limestone. Yeah, maybe you can. But in terms of comparing the cement, it is still sustainable, of course. How about the long-term performance? Because when we try to quantify the sustainability of the concrete, of course, we have to consider the whole life cycle of the concrete, yeah, not only how we produce that kind of concrete. So, do you have information about the durability of this concrete?
Okay, because this is still a very, even though this Lc3 is able to give good strength and is sustainable, but it is still not out in the market yet because of this durability issue, and we also acknowledge it, which is why we put it in our suggestions. Sean, can you go to the last slide?
Yes.
Okay, which is why in our suggestion is because this is still a material, so further studies have to look into this durability performance on its water absorption, shrinkage, and chloride resistance.
Okay, so no problem. I suppose that you have this concrete, this type of concrete, not you create this concrete not only for the purpose of this competition, because you also show in your slide that there is a publication of your concrete, yeah, before, yeah, is it right?
Yes.
Yeah, so you already work in this kind of concrete before this competition. It is right.
Yes, yes, because yeah, there's a research team in NUS using marine clay in concrete. So
Okay.
yeah, one part of it is this replacing cement.
Okay, so because you already work in this kind of concrete before this competition, I assume at least not maybe other team of yours in your group, the committee put restriction, yeah, in producing the concrete, yeah. So if there is no such restriction, do you have any modification of your concrete?
Sorry?
I mean that the committee put restriction, yeah, in making the concrete. For example, limiting the cement content and not using other type of certain material and so on. If there is no such restriction,
okay,
what will you do with your concrete?
Oh, okay. Wow, that's a very interesting question. I think one of the restriction was we cannot use was the capacity, was the maximum cement amount, which is at 300. So the committee only allows us to use the maximum cement content of 300 kg per meter cube. So of course, if we had no limit to that, we could have maybe used a higher. We could have changed the cement content that will balance
you need to put a higher cement content, because using 280 you already achieve your target.
Yeah, actually that's
maybe in terms of the slump, yeah, workability and so on, you can improve something. Because I think with the result of your slump test, it is very low, yeah. Only 80. So if you want to improve, if you have a second chance, and what will you do? Yeah, with your mix.
I think John previously mentioned in the mix design slide that we were trying to achieve 480 kg per meter cube of cementous materials. So we suspect the viscosity of the, or like through a few tests of a few trial mixes before, is that the increased usage of calcine clay and limestone would result in a lower viscosity, similar to what you said about the slump test. So I think what John meant when he said that but if we could redo this, I think we would want to increase our cement content while maintaining the 480 cementous materials, reducing our calcine clay usage. We should make our flowability and workability a bit better. Yeah.
Okay, so it is because of the use of calcium clay and limestone, which is finer compared to the OPC, that make the fresh properties very thick.
Yeah,
okay.
It was the very low water to cementitious material, so of a 0.3. So maybe yeah, we could have used a higher ratio of water to cementitious material.
Okay. Okay.
Yeah, we could change that also.
Okay. So as you said before, that this kind of concrete is not already in the market, yeah, still in the lab, yeah, research. So what is the next step that you can think of so that this concrete available in the market?
Sean, can you go to the suggestions?
Yeah.
Yes, sir. Of course, the further studies must look into the durability, performance, and also can find the optimum design mix, the point 3 of our suggestions. So and also the point 4, the consistency of our fresh concrete, because yes, our slump value is not very good. So yes, so these are the suggestions that we can look into.
I think in addition to that, to add on is like when we mentioned about the sustainable mortar comprising of that, I think we are also looking into 3D printing. Like I think that could be one of the usage for our clay. Because of its high slump, it would be rigid enough to be able to be pumped from a 3D printer for a 3D concrete concrete printer. So that's one of the ideas too. But it's just a suggestion.
Okay, thank you. I think my time is up.
Yep, thank you so much.
Okay, thank you very much, Professor Stefanus. Thank you so much. Thank you very much for the juries for the interview. This is the end of the interview session. Thank you very much for the Aeropile Drive team. You may leave the Zoom meeting room. Thank you very much. And the next thing who will present is Bakul, Beton, and 60.
10 minutes and I'll start it whenever you start to speak. After that, there will be a 30-minute interview. So without any further ado, for the Bakul Beton S62 team, the screen is yours.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Let us first thank the Almighty God for His blessing and grace that He has given to us so that we're able to attend this final stage of this competition. Good morning and greetings to the honorable judges and the committee of the International Concrete Competition. We thank the judges who have freed their busy schedule today and the committee who have managed to arrange such a wonderful event in this tough time, which have allowed us to bring forward our presentation today with the title of Caraka Concrete, Green Innovation Concrete using blood Cochleas, rice husk ash, and granite stone. Now, ladies and gentlemen, in the past few years, Indonesia have been constantly working on the building of infrastructure all over the nation. If we take a look at the heart of our nation in Jakarta, there is the LRT project in Jakarta. Moving up to the north, there is in Kalimantan, there is the construction of Balikpapan Samarinda Tollway. Going to the left, in Sumatra, there is the Palembang Tanjung Api-Api Tollway. Taking a cruise to Sulawesi, there is the elevated tollway of Petarani and Makassar. Going down south a bit, in Maluku, there is the Pulau Butu Island Road. Now, the previous construction of infrastructure are proof that Indonesia is a nation that fully supports and participates in the Sustainable Development Goals, or SDG in short, 2030 program. In particular, goal number 9 is very visible: sustainable innovation and infrastructure development. And realizing that 2030 is just right around the corner, the utilization of high early strength concrete to accelerate our construction progress is a way to make sure that we achieve this goal. Other than that, there's another important goal that we need to keep in mind. That is number 13, the fight against climate change. Now, why is it important? Well, it's because cement that we use as the main ingredient of building in infrastructure all over the nation is responsible for up to 8% of global carbon dioxide emission from its production process. Another problem is that despite being the main ingredient, cement is rather expensive. Now, cement aside, there is another problem in our nation that is not any less urgent. That problem is improper waste handling. In East Surabaya, in Kenjeran Beach in particular, there is a waste that piles up to 3 tons every week. And that waste is blood cooker shell. This waste comes not only from the sea, but also from the shell that is consumed by the local communities. Furthermore, it is reported that only 10% of this waste is processed further. And looking at other materials, as Indonesia has huge potential in reserve in non-metal resources that evenly distribute throughout the nation, one of which is granite stone, reserve totaling up to 10.7 billion tons. Tulungagung, in a district in East Java, is an example of granite craft hub that produce granite waste in handcraft production process. Other than granite stone, as Indonesia is an agrarian nation, we have high abundance of rice harvest each year. In East Java alone, rice harvest reaches up to 13 million tons in 2017, leaving rice husk when processed into ready-to-cook rice. From that, we are aware that we are in need of an innovation to obtain a concrete with high early strength compressed to sustain our development, but is still environmentally friendly, sustainable, and at the same time is able to minimize the construction costs.
Which is why, to answer the need, we, Bakul Beton S62, with me Zenfoy Vicky Mahendra, and my 2 friends, Andika Wahyu Eka Sakti and Bayu Prayoga Adianto, with our supervisor, Dr. Wahyu Niarsi Sutrisno, brought our innovation, that is Caraka Concrete, the green concrete using block cocoa shell S, rice husk S, and granite stone. So this is our innovation material that we use in Caraka Concrete. We substitute 25% of cement and change it with a block cocoa shell and rice husk S. So that is 12.5% each material. And then we substitute 60% of coarse aggregate and change it with granite stone. Of course, there will be a question, why we choosing this material? So the first reason is the evidence of material availability. As previously mentioned, 110% of block cocoa shell waste is processed and granite stone resource up to 10 billion tons, and the evidence of rice harvest that reach 30 million tons. Therefore, we can utilize them as a material that can substitute for concrete on a large scale. So the second reason is more environmentally friendly. So By using block cocoa shell rice husk ash, we can reduce the amount of cement that we use in concrete. Furthermore, it's also reduce the amount of block cocoa shell and rice husk ash waste. And the third reason is material content that is similar to substituent. Both of block cocoa shell and rice husk ash contain silica dioxide and calcium dioxide that is similar to cement, so they can be used instead of cement. So this is our processing method of block cocoa shell ash. The first step is material procurement. In this step, we procure material that is block cocoa shell, and then we dry it under the sun. We clean it. We cleaning the material. In this step, we clean the block cocoa shell from dirt and the other material, and then we dry the block cocoa shell under the sun. And after it dry, the block cocoa shell is ready to be mixed. Finally, using a ball mill, the material is mashed until it's past number 200 shift. And that's the result of those steps after we do all those steps. So the next processing method is rice husk ash. The first step is rice husk procurement, which is in this step we procure our material that is rice husk ash. Second, we dry the rice husk under the sun until it's dry. After it's dry, we proceed to burn the rice husk until it's charred. And lastly, after the material is burned, we mash it with ball mill until it's past number 200 shift. And that is the result of rice husk ash after we do all the steps above. So the next processing method is granite stone. The first step is material procurement, which is in this case is granite stone. The second, we shift the granite stone through the 20 millimeter shift, our coarse aggregate shift. For the stone that doesn't pass through the shift, it's mashed manually with hammer before it's being shifted through again. And after the result of granite stone can through the shift, we can see the result of the granite stone right here. So this is the research method for our charcoal concrete. The first step is to do a literature study and problem definition about our innovation material. And the second one is laboratory test and material preparation about our innovation material. And the third step is making charcoal concrete, which include the mix design and making the sample and doing the curing. And the next step is do the compressive strength test. If the results doesn't match our mix design, we have to repeat the previous step, making a new mix design. And if the results match with our design, we proceed to the next step, that is data analysis and literature comparison. And then we proceed to make a proposal based on our innovation and mix design that we created before. And finally, the conclusion, where we make a conclusion about our research that we have done before. So this is our charcoal concrete mix design. In this mix design, we use ACI based on Indonesian standard 7656/2012 with the compressive strength of 28 days old is 32.3 MPa, and the for 1 day old is 18 MPa. And this is our mix design compared with normal concrete. As we can see, there's two types of concrete has different in the amount of cement, where the innovation concrete has 299 kg per meter cubic, and the normal cement has 399 kg per meter cubic of cement. From there, we can conclude that charcoal concrete use less cement than normal cement.
Okay, so these are the one-day result of compressive strength test in charcoal concrete that we have done in ITS laboratory. As we can see, the average result of compressive strength test for 1 day old is 20.3 megapascal. So it's been reached our compressive strength target for 1 day, that is 18 megapascal. Okay, so we will continue with the analysis of life cycle cost and analysis of life cycle assessment. Analysis of life cycle assessment is conducted to find out what is the impact of using innovative material in charcoal concrete with the environment. And for the first material, it's block cocoa shell. It needs to be dry by placing it below the sun and mass using ball mill machine for 6 hours. And the ball mills needs 66 kilowatt hour of electricity energy for massing 50 tons of blood buckle shell. And the second material is rice husk. It needs to be dried by placing it below the sun, burns until it turns to ash, and mass using ball mill machine for 2 hours. And rice husk combustion process happen at 400 degrees Celsius, and it is around 650 kilojoule of energy for the process, which is needing less energy consumption than cement production. But after the combustion process, the rice husk still need to mass using ball mill machine for 2 hours, and the ball mills need 22 kilowatt hour of electricity energy for massing 50 tons of rice husk. And the third material is granite stone, and it doesn't require further processing, so granite stone doesn't produce any pollution. Now we will continue to the analysis of life cycle costs. And analysis of life cycle cost is conducted to compare the efficiency level in material production between making normal concrete and Caraka concrete. For the unit price of normal concrete material, we are using standard unit price of Surabaya City. And for the innovation material, we calculate the delivery cost of granite stone and the cost of electrical energy while using ball mill machine for blood buckle shell and rice husk. As we see from the calculation, there is a price difference of 157,000 rupiah for each meter concrete, which make Caraka concrete more economic than normal concrete. In conclusion, Caraka concrete is an innovative concrete as the result of optimization of cement and coarse aggregate substituent by using blood buckle shell waste, rice husk ash, and granite stone as the substituent to create a positive impact to the environment because it can reduce the usage of cement up to 99.96 kilogram and reduce the usage of split stone up to 598 kilogram for every meter cubic of concrete. The next one is Caraka concrete have a high early strength compressive strength that matches our target with a average of 20.3 megapascal for 1 day, and overall Caraka concrete can save up to 21% or 157,000 rupiah for every meter cubic of concrete. We have a couple of suggestions for those who wish to dive deeper into our research. The first one is further research is needed on blood buckle shell ash and rice husk ash as a binder to the characteristic of the concrete result. And the second one is it's necessary to check the use of blood buckle shell waste, rice husk ash, and granite stone in large production of concrete, so that the concept of environment-friendly innovative concrete can be applied. Okay, with that, we conclude our presentation for today. Thank you very much for your attention.
Okay, thank you very much for Bakul Beton Institute team. And now we will enter the interview session. And for this session, we divided to 3 sessions. There will be 10 minutes for each jury. For the first jury, Professor Dr. Abdul Rahman bin Mohsen, the time is yours.
Okay, thank you, Mr. Chairman. Thank you also. Your group is what? Bakul Beton. The
Yes.
name of the group.
Yeah, Bakul Beton.
Bakul Beton, sir. Yes.
Bakul Beton. S62. Nama pun very nice. Okay, and then you have this Caraka concrete, green innovation concrete using blood buckle shell, rice husk ash, and also granite waste. Okay, I just wondering, Caraka is what is meant by Caraka? Caraka concrete, Caraka. Concrete I know lah. Caraka? Can you hear me?
Loud and clear, sir. Philosophically, Caraka concrete means strong, and it means pretty much strong, a strong concrete.
Strong concrete lah, okay lah.
Yes.
So the word Caraka is from which word? Latin word ke? Indonesian word ke?
It's from Sanskerta.
Sanskrit.
Yes.
Oh, okay, alright. Alright, okay. So thank you. And then you use this blood buckle shell, rice husk ash, and also granite stone. To produce your sustainable concrete lah, I would say. Green innovation and also sustainable lah. Okay.
Yes, sir.
just wondering lah, you replace this blood cockle shell as cement, as part of the cement replacement material, okay?
Yes, sir.
So, what is the main composition of this blood cockle shell? Chemical composition there. Komposisi kimia. Blood cockle shell.
Yeah. Please give us a moment to present the slide for the chemical property of So here's the chemical property of blood cockle shell, which mainly with a high content of carbon oxide. So
calcium oxide.
Yes,
CaO.
carbon oxide and silica dioxide.
Not carbon oxide, CaO, calcium oxide.
Oh, calcium oxide. Yes, sorry.
Carbon C. Okay. Silica is just only what not even 1%. Kan 0.38%.
Yes.
Okay. So before the cockle shell ni dia get this CaO, calcium oxide. Okay. So initially it is calcium carbonate, isn't it?
Yes, sir.
Calcium carbonate, and then you have to process. You have to burn, isn't it? Because the cockle shell tu, if let's say you grind, and then you test the punya tu is the calcium carbonate.
Based on the journal that we have found, the calcium oxide will actually what do you call it? Will flourish in by the mashing and the reaction between water and the blood cockle shell.
That is the hydration process, chemical reaction. But the basic, the initial one is blood cockle shell is containing calcium carbonate. And then in order to get the CaO, you need to process, you need to burn the blood cockle shell, isn't it? The burning process.
For our particular, I guess, step, we do not need to burn it. And from the journal that we found, there is no particular specific steps that say that we need to burn it to, I guess.
Meaning you grind the blood cockle shell and then you directly use as cement replacement material.
Yes, we directly use the blood cockle shell as cement replacement. After we clean it, we grind it, and then we use it.
Yeah. You grind. So the chemical composition is the calcium carbonate. So you need to process that to get the CaO. Okay, all right. Okay, no problem. Okay, and then you use rice husk ash. Okay.
Yes.
So rice husk ash, the chemical composition that make it useful for cement replacement is what? The chemical composition of rice husk ash.
For the rice husk ash, the chemical composition is the majority of silica, sir.
Silica.
Silica with 82% of silica.
Okay, 82% silica. How to ensure that the silica can react? Because if let's say sand, normal sand is also silica, but it is not reactive. How to ensure that this silica from the rice husk ash is a reactive silica? Any idea how to?
For the rice husk, we still need to burn it until 400 degrees of Celsius, and as I found from journal, it said that the silica will the silica will reaction after it burns at 400 degrees Celsius.
So you have to burn this rice husk to at around 700 degrees Celsius to make the silica reactive.
To make the silica reactive.
Yes, that one lah. Okay, alright. And then you use also granite stone.
Yeah.
So in normal construction, do they use granite as coarse aggregate? No. Normal construction.
No, no, sir. They use Redstone in normal construction.
Yeah, because granite is natural resources, isn't it? Okay, natural resources. But
Yeah,
this
it's
is,
a natural resource.
you use as a like tile, isn't it? You make it tile, granite, again, granite stone, to make it tile. It is not the for the for the okay. And then you use the waste from the tile manufacturing,
Yes, yes.
Yeah.
Okay lah, alright. So that relate to the sustainability lah. Okay lah, Okay. And then what is your water cement ratio in your mix? Value of water cement ratio.
Wait, sir. We will prepare the here.
So this is our water to cement ratio, sir, from the table of innovation standard. We got our water to cement ratio is 0.510, 0.51.
0.51.
Yeah.
The target strength is what? 20
Target strength is 32.3 MPa.
32. So in between between 0.7.
Yeah, we need to interpolation the value.
Okay. All right. So that one is a water cement ratio or water cementitious ratio?
This is the cementitious ratio, sir.
So which mean that 300 plus dengan apa? Rice husk and also block Cochlea.
Cement, rice husk, and block Cochlea.
Okay. So we need to say that the water to cementitious ratio.
Cementitious ratio, yes, sir.
Okay. So what do you think that in the future use of your invention here?
Mainly because we utilize ordinary Portland cement, which are not really compatible for mass concreting. We believe that the main use is for a small scale of column, a small sized column that can be, I guess, mixed in like 2 or 3 segments, and so just bit by bit. So that is the main use of our innovation shop for a main small size column.
That the future application is very vast lah, sangat luas lah. Is for the applicability. So overall lah, just overall. So in terms of the waste ni, the one that you shown rice husk S, and then black Cochlea and also the granite stone, the waste from the granite stone production, that one, okay. Will that be able to cover in terms of the need for the construction industry in at least in Indonesia lah?
Yes, sir. So for the, I guess in particular the rice husk, we will definitely be able to cover as the 13 million tons of production each year, and for the granite stone, the reserve totaling up to 10.7 billion tons, and for the blood Cochlea, we like receive 3 tons of new material each week, sir, in Kenjeran Beach alone. So yes.
Okay, all right. Okay, so thank you much. So meaning to say there's a future for your innovation lah. All right, so thank you very much, group Bakul Beton.
Bakul Beton, sir. Thank you for your answer.
Thank you very much.
Thank you very much, sir.
Okay, thank you very much for Professor Dr. Abdul Rahman bin Mohsen for the questions. Now we're gonna move to the second jury, Mr. Iwan Supriyanto. The time is yours.
Okay, thank you. Can you go back to the slide of mixed proportion? The mixed proportion of. Okay, this one.
Yes.
How you determine the water you use in the mix? This is 203 kg.
203. Okay.
Yeah. How you determine the water? The water cement, your water cement ratio is.
Okay. So to determine the free water content or free moisture content and air content, we use this table, sir, from the Indonesian standard. From this, we can calculate the free moisture content by the interpolation result.
What is the slum result?
Yeah, by the slum result and maximum normal aggregate coarse aggregate size.
I mean your actual slum result of this research.
Oh, the actual slum for our research is hold on. This is our slum test. From the results, we got 140 millimeter from the slum test.
After adding the SP?
Yeah, it's after adding the SP.
Chemical?
Yeah.
Before or after adding?
After we use the SP, sir. 0.8% superposition.
Only
system.
14?
Yeah, 14 millimeter for slum test.
Okay. The
14
blood buccal rise. Yeah. You use this material as a supplementary of cementing or supplementary of natural sand?
Can you please repeat that, sir?
Can you go to the result that the percentage of its material? Yes. For blood sugar cell, you use this material as cementing, supplementary cementing material, or supplementary of natural sand.
We use the blood cell for cement substituent, sir.
Cement?
To replace the cement, yeah.
How you decide the percentage of 12.5%?
For the particular the exact percentage, we
Can you show the
from
slide?
the journal. Yeah.
Can you show the
Please go to the journal.
The result before you decide the 12.5% of cement or of sand? The 12.5%
of cement, sir.
Of cement.
12.5%.
I saw your table. Can you show the background or your research before you decide the 12? How you decide the 12.5%? What is the research behind that? Why don't you use 12, 20, 25, or 30? Now this one. Okay.
Yeah, this one, sir.
So this material as supplementary cementing, right?
Yes, sir.
Why your research combine this material with sand? Why don't with cement?
Oh, okay. So to clarify, sir, we utilize blood Cochleas and rice husk ash as cementitious material, right? So
yeah.
In overall, we take away 25% of the cement and replace it with 12.5 each of blood Cochleas and rice husk ash. And where we got this number is first from a journal from literature study, and where we found the most optimal number for blood Cochleas is around 10 and 20%. And then we combined it with another journal of rice husk ash that we have, which also numbers around 10 to 15. And from there, we trial and for for the paste, for the mortar in particular, for the different composition of blood Cochleas and rice husk ash. And then from there, we found out that the most optimal for both our, criteria for the maximum of 300 cement that we use, and for the compressive strength of the high early compressive strength is the most optimal is 12.5 for each of them.
I mean, if you use this material as because it has a calcium oxide very high, yeah.
Yes, sir.
But why in this slide you combine with sand?
Oh, okay. So
the percentage taken from total sand, right? Total
no,
fan aggregate,
cement. cement.
This one?
Cement.
100 cement, 90% pasir plus 10% kerang.
Oh, sir. From this in particular, we found this one is not from. We just use this for a table of reference as to how many percentage of blood cooker shell is the most optimal. But in our concrete in particular, we don't change the blood cooker shell with sand. So the sand composition is still 100% still. We do not substitute it with anything else. So perhaps this table is making, I guess, a misunderstanding.
Yeah, that's why I'm asking, because your research, the combination with sand and okay. Then you go back to the LCC and LCA slide. Okay. I think this is good slide. How you determine the energy consumption?
We calculate it. Wait, we will change the slide.
This one.
Yeah, this one. For the blood cooker shell, we are using a bombing machine type CDBY 1230, and it needs a motor power of 11 kilowatt. And the duration for blood cooker shell process is 6 hours. And we calculate it, and we have 66 kilowatt hours for 50 tons blood cooker shell. And for the cement, we found it in journal that the energy consumption of a modern cement plant is about 110 kilowatt hour for each ton of cement. And next, for the risers, we calculate the energy of combustion process for each 1 kilogram of risers with the CF rates of 0.42 kilocalorie per kilogram Celsius. And for the temperature of rice husk, we need to combustion it until the temperature of 400 degrees Celsius. And here is the energy of combustion process. It's 649 kilojoule. And for the cement combustion process, we do the same calculation, but we have a different temperature, and we found it from the website Cement Indonesia, that it said that the temperature of cement combustion is 1,500 degrees Celsius, and for the from the calculation we have 1,352 kilojoule. Okay, next.
Okay. I think this, if I want to use this, your research for mass production, yeah, in actual condition.
Yes, yes. Sir.
Can you explain what kind of resources or equipment that I have to prepare? Do we have resources of raw material if I want to use for mass production?
Yes, sir. So for the natural resources in particular, for the blood cooker shell in Indonesia, we have plenty of, I guess, beach in our nation. We are an archipelago nation. So the natural richness of our seas is very high. So the amount of blood cooker shell waste that is produced from every beach is really high. And from the rice, we have 13 million tons for each year in East Java alone. And the granite, we have 10.7 billion tons of reserve in Indonesia in particular.
Okay, okay. My time is up. Okay, thank you. Good.
Thank you very much, sir.
Thank you very much, sir.
Okay, thank you so much for Mr. Iwan Supriyanto for the questions. Now we're going to move to the third jury. For Professor Stefanus Adi Kristiawan, ST PhD, the time is yours.
Okay, thank you. I would like to discuss with this team about their innovation for using the blood cockle cells and rice husk, yeah, as cementitious
material. Yes, sir.
Material, yeah, okay. So can you explain the contribution of this cementitious material in terms of your strength?
Okay, so first of all, to answer your first, I guess, discussion to start it, from the blood cockle shell with high abundance of carbon oxide, we found out that a higher carbon oxide content in concrete, the faster, the higher, I guess, the faster the setting time of the concrete itself. So by increasing the amount of carbon oxide in our concrete, we expect the concrete setting time to, I guess, further accelerate, such increasing the high early strength of our concrete. Now, moving to the rice husk ash. Wait, please hold on, sir.
Okay, no problem.
For the granite stone first, as the specific gravity of the granite stone is higher than regular split stone, which reach up to 3 gram for each centimeter cubic. We expect it to increase the density as well as the porosity and durability in overall of our concrete. So by having a lower abrasion and higher density, we expect for the overall durability of our concrete to be increased by using granite stone. And lastly, for the rice husk ash, so for the rice husk ash, we expect it to further react with I guess a chemical substance called portlandite. Portlandite is a chemical substance that is produced by the reaction of pellet and water, which is cement plus water, which produce CSH or concrete. So by adding more silica in particular, we expect for the portlandite to react with the rice husk ash to produce more concrete or CHH.
Okay, thank you. Can you go back to the first contribution of the calcium oxide of your blood cockle cells? I use from this, you are using this figure to show that the calcium oxide have a contribution in the setting time, yeah, so that the concrete will get faster strength, early strength. Is it right?
Yeah, strength, sir. Yeah.
So do you think that the calcium oxide from the blood cockle cell that you have can it is active material? Do you understand what my question? It means that when you mix it with the water and then it can react by itself.
Yes, sir. So for the blood Cochleas in particular, we add it after we do the mixing in our concrete. So first of all, we added the aggregate, the sand, as well as the cementitious of rice husk gas and cement first. And then we start the mixing, adding some water. After the solution, I guess the mix is somewhat heterogeneous or homogeneous, sorry, somewhat mixed, blend perfectly. We then proceed to add the blood Cochleas. So which in hope this carbon oxide will accelerate the setting time of our concrete. So that's how, sir.
In what way the carbon oxide can accelerate the setting time?
Yes, sir. Because with higher calcium content in concrete, it will increase the temperature of the initial setting time of the concrete. So it increases the speed, I suppose, of the reaction of the hydration of concrete.
So it means that when the your powder of the blood cochlear cell put into water, it can produce high temperature.
If we put the calcium oxide and water alone, no, sir. But if we mix it with concrete, we believe so, yes.
So how do you sure that it is come from the CRO of the blood cochlear cell, not from the cement?
For that, I guess the one sure way to I guess to know whether the carbon oxide contributes on the setting time is to do compressive, I guess a comparison between compressive strengths, sir. And from if my friend will kindly move to the slides of double conversion, please. Yes, so from our previous test for the normal concrete or the control concrete, which have the same mixed design as well as the higher cement content, we found that the 1 day old of the compressive strength only reached up to 8 to 9 megapascal from a couple of trials. And from a literature study, we found that the 1 day old of a regular concrete only reach up to 0.231 of its 28 days old, I guess, compressive strength. And by calculation, a simple calculation, the 1 day old strength of the 32.3 megapascal mixed design for normal concrete reach only up to 7.5 megapascal. On the other hand, our concrete, we have the higher compressive strength that reach up to 20.3 MPa, which is 2.7 times higher, or I guess faster in this regards of setting time.
Okay, because time is limited, I want to move into the granite stone. If I'm not mistaken, you mentioned that using this granite stone, then you can expect to have a more durable concrete. Why?
So for the granite stone, because higher specific gravity means I guess the granite stone is more compact than regular split stone, sir. So
yes,
we can expect it to
overall,
be more
dense. But overall, when you talk about concrete, it is not about the absorption of the aggregate itself, but the matrix base, yeah, because
yes,
the absorption of the any type of the aggregate with compared to the matrix, of course, it is better, yeah.
Yes, sir.
So any improvement of the aggregate part will not change very much in terms of the durability, because the main point is about the metric. Yeah.
Yes, sir. I guess other than the reason why we choose granite stone is because it is not that detrimental to the overall compressive strength, but at the same time, it is a natural resources and a waste that is available in our region.
Okay.
So yes, sir.
Okay, thank you.
Okay, thank you very much for Mr. Professor Stefanus Adi Kristiawan. And that was the last for the interview sessions. Thank you very much for the Bakul Beton S62 team. You may leave the Zoom meeting. Thank you.
Yep. Thank you very much for the
Thank you
community
very much
for arranging such wonderful event. And once again, thank you for the judges who have given their time for today. Once again, thank you, and we are signing off.
Okay, the next team will present is Semar Adhideva team from Sebelas Maret University. Its members consist of Muhammad Naufal Muslim, Ganesha Wibisanulubis, and Maulana Kangko Wicaksono. I would like to remind you that your time for delivering the presentation is 15 minutes, and it started whenever you start to speak. After that, there will be a 30 minutes interview. So without further ado, for the Semar Adhideva team, the screen is yours.
Assalamualaikum warahmatullahi wabarakatuh. Greeting to all of us. Om Swastiastu, Namo Buddhaya. To the honorable juries and all the audiences, introducing, we are team Semar Adhideva from Sebelas Maret University. My name is Muhammad Naufal Muslim.
My name is Ganesha Wibisanulubis.
My name is Maulana Kangko Wicaksono.
And also our supervisor, Mr. Halon Alvisa and Mr. Suito.
Background. In 2017, national concrete production reached up to 137 million tons, and it predicts to increase every year because the concrete material has so many benefits compared to other construction material. International Energy Authority says that the amount of carbon dioxide in the world is reached up to 51 billion tons in 2017, and the cement industry contributes for about 8% from the whole amount of carbon dioxide in the world. It means that the production of the cement is producing 4 billion tons carbon dioxide. It can be dangerous for the environment. Next. In this point of time, we need the concrete material that are able to provide quality as planned in short quality of period of time, so that the construction process may take a shorter time, and we need the material that suit from the concrete work and tight rebar. Self-compacting concrete is the solution because it can flow and compact itself to every corner of structural construction that hard reached by the worker, and it can flow without having segregation. One type of the concrete that is often to use in short infrastructure project is high-strength self-compacting concrete. High-strength self-compacting concrete can decrease the difficulty in construction project, can decrease the use of energy, and can increase the quality of the concrete material. Next. There are the concept of self-compacting concrete are first adding more binder and more powder, reducing water content and cost aggregate, and using super plasticizer to get good result of slump flow test and compressive strength of the concrete. And this is the comparison between the material from self-compacting concrete and conventional concrete. Next. However, high-strength self-compacting concrete with use more powder and more cement, it can be dangerous for the environment. Therefore, we should have changed this material into alternative material that environmentally friendly, lower cost, and sustainable. Next. Therefore, we are from Smart Adhideva team, Sebelas Maret University, over some innovation. Our innovation is eco-friendly, high-strength, self-compacting concrete using Metacolin as geopolymer binder, limestone as partial substitution of cement, and waste marble dust as partial substitution of fine aggregate. Next.
Next, here are the materials used in our innovation concrete. First, we have the Merapi crushed gravel as one of the coarse aggregates. Second, we use ordinary Portland cement. Third, we use Merapi sand as one of the fine aggregates. Fourth, water. Fifth, the super plasticizer product used is Viscocrete 1003. And last, our innovation materials, which are Metacolin as the geopolymer, waste marble dust as the partial substitution of fine aggregates, and limestone powder as the partial substitution of cement. Next, geopolymer. Geopolymer concrete is a concrete with binder made up of materials containing silica and alumina that is activated with an alkaline activator in the form of sodium hydroxide and sodium silicate. Sodium silicate, which has the function to speed up the polymerization reaction. And as for the sodium hydroxide, it has the function to help the binding process between particles. Next.
Metacolin. Metacolin is another pozzolanic material which is manufactured from solid kaolin. Metacolin is obtained from cement village, Gunung Kidul. Metacolin are containing pozzolan compound silica alumina oxide more than 60%, which can be used as binder for geopolymer concrete reacted by sodium silicate activator and sodium hydroxide solution. So it is a reactive pozzolan that useful to increase the quality of the concrete. Next. Next is limestone powder. Limestone is a commonly type of carbonate sedimentary rock. It composed mostly the mineral of calcium and argonite. As we can see, the calcium carbonate in the limestone powder is the potential use for our innovation concrete. The main benefit while we using limestone powder is an accelerator for cement hydration to help nucleation, which is able to increase the early compressive of strength of the concrete. Next. The next is waste marble dust. Waste marble dust is created as byproduct during cutting of marble. As we can see that calcium oxide in waste marble dust is the potential use for our innovation concrete. As we know that the calcium oxide is the one of the main material in the making of cement, which is a clinker. So waste marble dust can be used to increase binding distribution just like cement. Next.
Next is about the alkali activator solution. Alkali activator solution used in the study are sodium silicate and sodium hydroxide. 12 molar of sodium hydroxide solution is mixed with sodium silicate solution to reach a ratio of 1.5. In our mixed design, the total weight of alkali activator used is 25% of the geopolymer. Next. Here we can see that the geopolymer reaction is different from the ordinary Portland cement reaction. The left image shows about the reaction of a Portland cement, as for the right image shows the reaction of a geopolymer. Geopolymer does not form calcium silicate hydrates to create its matrix and strength, but is obtained from the polycondensation of silica and alumina precursors and high alkali content to achieve its structural strength. Next. Other than that, if the Metacolin has not reacted perfectly, the silica content in the Metacolin powder can be used as a secondary reaction, or we call it pozzolanic reaction. It can be seen that the reaction above is the reaction produced by the cement. One of the side reactions resulting from the cement reaction is calcium hydroxide. This calcium hydroxide, when bonding with oxygen, can have a negative impact on the concrete in the form of void or cavities in the concrete. Therefore, when the silica content from the Metacolin bind with calcium hydroxide, it can prevent our concrete from having cavities or void. Next. And here are the research methodology that we use in this study. First, we need to find the formulation to the problem. Second, we need to find the literature as the basis of the research. Third, we need to create several mixed designs to be tested. Then we perform several trials using different compositions. Next, we should find the best composition we need based on the trials that we need. After that, we perform our final mix using the best compositions. And finally, we should be able to test our one-day compressive strength and test the slump flow. Next.
We have conducted several trials with different material proportion. Here, we conducted a trial with a comparison of the proportion of binders between cement, geopolymer metacolin, and limestone powder. It can be seen on the table that we get the most optimal proportion for the compressive strength and slump flow test at a proportion of 60% cement, 30% geopolymer metacolin, and 10% limestone powder. And we conducted a trial with the comparison of the proportion of aggregate between sand, marble dust, and coarse. It can also be seen on the table that we get the most optimal proportion for the compressive strength and slump flow test at a proportion of 25% sand, 30% marble dust, and 45% coarse.
And next, here are the mixed design that we use in the making of our innovation concrete. This mixed design refers to ACI and F-notch with a target of 60 megapascal in 28 days. The water cement ratio used is 0.28. The metacolin used as geopolymer binder is 30% of the cemented fuse binder. The limestone used is 10% of the cemented fuse binder. As for the waste marble dust used is 30% of the total aggregates. Comparison of fine aggregates and coarse aggregates are 55 comparing to 45. And last, the super plasticizer used is 1.5% of the cemented fuse binder. Next.
Our innovation concrete has a slump flow value of 65 centimeters and 67 centimeters with an average of 66 centimeters. It can be concluded that our innovation concrete qualifies as self-compacting concrete. And here are the compressive strength results of our innovation concrete at the end of one day. Of the 3 concretes we made, we produced a compressive strength of 30.65 megapascal, 29.86 megapascal, and 31.92 megapascal, with an average of 31.81 megapascal.
And here are the analysis of Lifecycle assessment for our innovation concrete. Here we can see that the amount of carbon dioxide emission for normal SEC is about 1,371.89 kilograms per cubic meters. But by using our innovation SEC, the amount of carbon dioxide that is produced is only 1,127.02 kilograms per cubic meters. Therefore, by using our innovation SEC, we can save the amount of produced carbon dioxide by 244.87 kilograms per cubic meters, which is 18% comparing to normal SEC. In the other hand, our innovation concrete is also environmentally friendly. It can decrease the amount of air pollution and dust pollution that is bad for our respiratory systems. It can also reduce the bad effect of sand mining, which can disturb the ecosystem and water pollutions. Next.
Here is the analysis of life cycle cost of our innovation concrete. Here the price we got from using our innovation material is 1,074,000 per cubic meter. It is known that by using our innovation concrete, we can reduce production cost by 194,000 per cubic meter, or save around 15% compared to non-innovation concrete, and also reduce the production cost by 125,000 per cubic meter, or save around 10% compared to K600 ready-mix concrete. In determining our innovation material, Semar Adhideva team also pays attention to its availability so that our innovation concrete can be produced massively. And the first is the availability of Metacolin. Based on BPS, the potential for kaolin reserve in Indonesia is estimated at 66.21 million tons. that is spread around several areas such as Kalimantan, Bangka Belitung, and Java. And second, the availability of limestone powder. According to LPPD, the potential of limestone is estimated at 3.59 billion meter cubic. The amount of limestone is spread over an area of 4,130 hectares. And third is the availability of marble dust. Waste marble dust is generated as a byproduct during cutting of marble. The waste is approximately in the range of 40% of the total marble handled. From the data shown, it can be seen that there are a lot of metacolin, limestone powder, and waste marble dust that until now has not been optimal utilization. That is what makes us use those material as a mixture in our innovation concrete.
From the explanation that has already been said, we can conclude that our innovation concrete is very eco-friendly because we use waste material that can decrease the amount of environmental pollution, and it can reduce the production of carbon dioxide by 80%. Other than that, from our innovation concrete, we conclude a slump flow test with the value average of 66 centimeter and have the one compressive strength with the average value of 30.8 megapascal. And it means that our innovation concrete qualified as high early strength concrete. Our innovation concrete is very economical because it can reduce the cost production by 15% compared to non-innovation concrete. So we need the support and the help from the judges so we can be more patient in developing our innovation for greater good. Thank you for your attention. We apologize if we still have a lot of mistakes. Inshallah, we will continue the progress in the future. Billahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh. Thank you everyone for your attention.
Thank you very much for Semar Adhideva team. We will enter the interview session for the honorable juries. The time is yours. First, Professor Abdul Rahman bin Morsam. The time is yours.
Okay, thank you, Semar Adhideva. Okay, all right. So your title is eco-friendly. Yeah, panjang, very long title. Eco-friendly, high strength, self-compacting concrete using Metacolin, blah 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 blah. Very long title. Okay. You use geopolymer binder for the concrete. So your concrete is geopolymer concrete or normal concrete?
So in our study, the Metacolin is used as a substitution, and it is replaced as a geopolymer concrete.
You mean you use sodium hydroxide, sodium silicate, okay? So that is geopolymer, okay? So yes, there's two things, geopolymer concrete and concrete is two different things. Geopolymer concrete means it doesn't contain any cement. So in your case, you have also cement also, isn't it? Yes, so that's why I'm asking whether your concrete is geopolymer concrete or polymer concrete. If let's say we use polymer concrete, so we use polymer and also we use cement. Okay, so that one a bit confused to me lah, whether you use geopolymer concrete or concrete, normal concrete. Okay, and then you use Metacolin. To get Metacolin, the initial material is kaolin, isn't it? And then you heat to 700 or 800 degrees Celsius, something like that, to make it Metacolin. And then this kaolin is all very expensive. I would say, if let's say in Malaysia, it's expensive. It's an expensive material. I'm not sure in Indonesia. Okay. Because now the kita punya theme is sustainability, so it relates to the cost and it also relate to the environment. Okay. So is the Metacolin is purposely for the geopolymer binder or for the concrete reaction, cement reaction? The Metacolin.
Okay, I would like to answer the question.
Okay.
So the Metacolin used in our concrete is as a geopolymer concrete. So it is also used to be a substitute of partial cement, sir. And we also use cement as a binder. And also the Metacolin is used as a binder also, sir.
So how you differentiate for this Metacolin? How many percent that it contribute to the geopolymer binder? How many percent that it contribute to the cement reaction? Is there any way that we can determine that?
So in our concrete, the geopolymer and the cement will end up as one, sir. Because maybe the difference is just on the making part of the geopolymer, sir. So first we need to create the geopolymer first by using our alkali activators mixed with the Metacolin, and then we will mix it with the cement, water, and other materials, sir.
Okay, so meaning to say that your concrete is a new concrete now. It is not normal geopolymer concrete. I don't know, geopolymer combined with normal concrete. I don't know, there's new name, I think. Yeah, because the term geopolymer is concrete without cement. Yeah. Okay, all right. And then you use this limestone also as partial cement replacement. Limestone, Okay, so which means that you have Metacolin, you have limestone as partial cement replacement. Okay. So which one which one is more say reactive, limestone or Metacolin?
Sorry, sir. I would like to answer the question again. So for us, the more reactive binder is the Metacolin, sir, rather than the limestone. Yes, sir.
So and then what is the thing that contribute to the early strength? One day strength you get the 30 and very high strength is 130. There's one day is already normal strength concrete.
Yeah. Thank you, sir. I would like to answer your question. This is a Metacolin is pozzolanic material that capable to partial cement substitution. Pozzolanic material which is contain high content of silica alumina. But for the early strength, we need to add limestone powder with marble dust, which is had chemical comparison calcium oxide and calcium carbonate. This is any study literature says that the calcium carbonate and calcium oxide can increase the early compressive strength of concrete.
Okay, marble dust, is there any reaction inside the mix, marble dust?
Marble dust we use for substitution of fine aggregate, sir.
So there is no reaction, isn't it? There is no reaction inside the concrete mix.
Yes, sir. It's a reaction because the calcium oxide and calcium carbonate makes the 3-calcium silicate hydrate. It is the one day on compressive strength is the point of calcium carbonate and calcium oxide sir.
So if let's say marble dust kan, base marble dust, if let's say base marble dust react, so we cannot use classify it as a fine aggregate replacement, because aggregate inside our concrete, aggregate is an inert material. Dia tidak belas, it doesn't react. Aggregate is just as a filler.
Yes, sir.
Okay. But if let's say the one that we replace as aggregate and then it react, it doesn't comply with the definition of aggregate.
Yes, sir. I
So
would
it
like
seems
to...
that your geopolymer, your metacolin, limestone, and waste marble also all react inside the concrete mix.
Yes, sir. The main point of adding marble dust in our innovation concrete, this is a filler, sir, which can increase the homogeneity and compactness of our innovation concrete. By using waste marble dust, it can also increase the early compressive strength because the calcium oxide in waste marble dust then can trigger tricalcium silicate hydrate compound. As we know that tricalcium silicate hydrate compound has the function to hardness in fail or early hours, so that it can speed up the setting time, sir. Setting time of the concrete.
The marble dust, if let's say it reacts, it cannot be classified as a sand replacement, because again sand is aggregate, isn't it? Fine aggregate is aggregate, kan? So it will not react. It is acting as a filler. So if let's say this marble dust, that's a reaction inside the mix, then it cannot be classified as a sand replacement. Okay, so that is the basic fundamental theory lah. Okay, probably my last question lah. You use self-compacting. So what is the purpose of using this self-compacting concrete? The purpose of using self-compacting concrete instead of just normal plain concrete?
Okay, thank you, sir. I would like to answer your question. Yes, the sustainability of innovation of the time, self-compacting concrete, has a high strength in early age, sir. So their innovation concrete can be used after 5 days from the casting process, where ordinary concrete has to wait to 28 days before ready to use. The application of innovation concrete is for urgent construction, sir, like the same in this competition, such as current pandemic situation, like right now. We have to build a hospital quickly so that can be used. Besides that, our innovation concrete has very high compressive strength. It can also apply for girder, piles, railroad, or precast industry, sir.
Okay, all right. Okay, thank you. So basically, okay, my time's up. Okay, just comment. Self-compacting is how to relate to the sustainability, that you have less workers, you have less work. That is the purpose of self-compacting. So in terms of the strength, it depends on the mix, the type of cement and so on. Okay, so thank you very much, Semar Adhideva. All right, so thank you.
Thank you very much,
Sir Abdul Rahman, for your advice.
Thank you very much, Professor Abdul Rahman. It's enough for the first jury. Moving to second jury, Mr. Iwan.
Okay.
The time is yours.
Thank you. Can you show again your slide presentation?
Yes, sir. We will slide this our presentation. Which page, sir?
Slide of Metacolin. Again, go back again. Okay, this persoalan. Okay, for Metacolin, yeah, have you done some testing to ensure that Metacolin has pozzolanic reactivity and strength index of this material? The pozzolanic reactivity, we have the data, and also strength activity index of this Metacolin. You use this material as supplementary cementing material, right? Yes. Containing pozzolanic properties. What is the pozzolanic properties of this material?
Okay, sir, I would like to answer the question. So
Can you explain about pozzolanic properties of this material?
Okay, sir. So, in about the Metacolin, so we have done several research and several trial mixing about the composition of Metacolin. And for the pozzolanic materials or the pozzolanic compositions, the pozzolanic materials in Metacolins are silica and alumina, sir.
I'm sorry, sir.
Silica?
I was like,
Silica and alumina?
yes.
What is the silica content in percentage, in average?
It is 61.97% for the silica.
Okay.
And for the alumina, it is only 16.34%.
Okay, so the most chemical content is silica, yeah?
Yes, sir.
Okay. And then next slide. Limestone. What is the most chemical content? Calcium.
Yes, sir. Calcium carbonate, sir. This is the main
Calcium
material in the
carbonate, right?
making of cement.
This is
cement,
also substitution of cement.
Yes, sir.
Okay. And the next one, West marble. The highest content is calcium oxide.
Yes, sir.
But you use this material as fine aggregate displacement.
Yes,
Why
sir.
you decide to use this material as a fine aggregate displacement instead of cement displacement, since this material has a higher calcium oxide content? Why you decide to use this material as filler instead of binder?
Yes, Mr. I would like to answer the question. In determining our innovation material, we have conducted several trial and literature study. And in literature study, we found a lot of study use waste marble dust as substitute for cement because it is capable of binding. All of the studies state that waste marble dust will decrease concrete compressive strength in the late age because it will dilute the calcium silicate and tricalcium silicate, different from the study that use waste marble dust as a substitute for fine aggregate. State that waste marble dust has many advantages such as porosity, increasing workability, and increasing react compressive strength. And the main point of adding marble dust in our innovation concrete is a filler, which can increase the homogeneous and compactness of the concrete. By using marble dust, it can also increase early compressive strength of concrete because of its calcium oxide in the marble dust that can trigger the calcium silicate hydrate compound.
Okay, yeah. From these three of innovative material, which one the most contributing in your one-day strike? This one.
The one of our innovation material that contribute for early strength, compressive strength is waste marble dust and limestone, sir. Because
but marble dust you put as a filler, not binder.
So the reason
this one,
why.
Okay, please explain the chemical reaction. Which one the first reaction and which one the secondary reaction for long-term strength and early strength and long-term strength? This one.
So I would like to answer to the question. So I think for the most contribute in the early age is the limestone powder, sir, because it has calcium oxide in its property, which this calcium oxide can create 3 calcium silicate hydrates, sir. As we know that 3 calcium silicate hydrates has a contribute in the making of the concrete a better early age strength, sir. And for the late age strength, the Metacolin has the contribute in the late age strength, sir, because this Metacolin has silica in its composition, sir, which this silica can be used as a secondary pozzolan reaction, sir, with the carbon hydroxide from the cement. So the silica and the carbon hydroxide cement from the cement can react and create 3 calcium silicate hydrates also, sir.
Okay. Do you have a result of how what is the difference of physical properties of normal concrete and this geopolymer concrete? The comparison of physical properties, hardened concrete in terms of strength, in terms of other properties of hardened concrete, of these two compared to normal concrete.
Okay, sir. So I would like to answer
the
question.
You can continue the result of the. I think this is very good result, yeah. But I want to please show your slide of LCC. LCC, can you show the slide?
Yes.
LCC cost. The cost comparison.
Yeah. Yes, sir.
Please show your slide.
Wait.
Can you open your slide?
Yes.
And go to
LCC.
Slide of LCC. The cost comparison. How you determine the cost of marble, Metacolin? Okay, this one. Go back. Yeah. How you determine the cost of waste marble, Metacolin, and limestone powder? How you get the cost per kg?
Yes, sir.
Okay, sir. So I would like to answer the answer. So we know that in our experiment, the cost of waste marble dust is assumed at 132 rupiah.
It should be calculated from whole process, right?
Yes.
So I want to know how you determine the cost
Okay, sir.
kg of these 3 material.
This cost is included transport, which costs 52 rupiah, sir, and the grinding cost about 80 rupiah. Therefore, we can conclude that the price of waste marble dust is assumed at 132 rupiah. As for the Metacolin, we assume it as much as 732 rupiah.
So you have the detailed calculation of
Yes,
this, yeah?
Yes, sir.
Okay.
We already cost include kaolin with the price, transport, and grinding cost, and burning cost, sir. We already calculated it.
Okay. Next time you show in this slide, yeah, so we can know the detailed calculation. Okay, my time is up.
Okay, sir. Thank you, sir.
Thank you, sir, for your advice.
Thank you very much, Mr. Ivan. It is now for the second session, moving to the last session. Professor Stefanus, the time is yours.
Thank you, the committee, and I would like to raise a question to this group. It is interesting that you have something new about your concrete. What do you call it? Hybrid concrete? Because it is combination of the geopolymer concrete and yes, we call normal concrete, and then between the two. My first question is, yeah, you choose Metacolin as the material that you will activate with. What is your activator?
Sodium hydroxide and sodium silicate, sir.
Okay.
For the alkali activators.
Okay. Because actually you have other cementitious material, yeah, marble dust, and also what?
Limestone, sir.
Limestone, sir.
Oh yes, limestone. Yeah. So why you choose the metacolin that you would like to activate to make a geopolymer instead of the other material?
So in this study, as we described earlier, we conducted several studies and several trials. Then our conclusion is that Metacolin is one of the best composition that we use in this study, sir. That is why we use the Metacolin as the geopolymer.
You already have or you already made a trial for
Yes.
the other. Okay, it's not success.
For the geopolymer, 100% is not success, sir. We success at 30%, sir, and we use in this competition.
Okay, so can you distinguish, yeah, or how do you differentiate between the contribution of the geopolymer and the hydration of the cement in terms of the strength development?
So to differentiate, actually for the reaction, we found it on a literature, sir. So the difference between normal Portland cement and geopolymer is different in the reaction, sir. Because for cement, we need it needs to create calcium silicate hydrates to create its matrix and strength, sir. But for the geopolymers, it only needs silica and alumina precursors, and with the help of alkali activators to achieve its structural strength, sir.
Yes. My question is that put geopolymer and also OPC cement, yeah, contribute to the strength development. Okay. Yeah, put contribute, of course, but in this case, how can you differentiate between 30% 30 megapascal of your early strength is contribute somehow by the geopolymer and the OPC hydration?
So as we said earlier, that we did several trials, sir. We did OPC 100%, Metacolin 100%, and limestone powder is also one of the materials that are used in our trials, sir. So we did several trials, and as we can see that from the presentation, that the optimum compressive strength that we get is by using 30% of the Metacolin.
I'm sorry, sir. I would like to add up the answer, sir. Yes, calcium oxide and silica oxide can form one of calcium silicate hydrate, sir, which is concrete constitute compounds that function and additive, sir. The more quantity with the ADC, the higher the strength and the resulting of the concrete. In this study, Metacolin, which is contain silica, is used so that the limestone powder and waste marble dust can be reactive and can increase the early compressive strength of the concrete, sir.
Okay. So the 30 megapascal is result of the many trials. Yeah. Okay. Okay. So I like to move to the question regarding the cost. Yeah. What if you saw the slide, yeah, about the cost, yeah. It is actually unit price, yeah. Unit price of the cost, not LCC. Yeah. Do you know the difference between the LCC and unit price?
Okay, sir. This is the life cycle cost, sir. In this the unit price that can be able to analysis life cycle cost, sir.
How do you correlate between the unit price and the life cycle cost? Because if you like to analyze the LCC, you have to consider the durability because it will affect the maintenance costs, yeah, and so on, yeah, during the whole service life of this concrete. So the initial cost, which is the production cost, not always resulting in the cheaper LCC, yeah, cheaper cost in terms of LCC.
Okay, sir. I would like to answer your question. This is the cost recalculation of our innovation material that cheaper than non-innovation material or ready-mix K600 concrete cost, sir. And this is the relationship because our innovation concrete is more cheap, sir, and have durability and have high early strength, compressive strength, and high workability, sir.
Yeah, I mean, yeah, you still consider the maintenance cost, yeah, and the maintenance cost will be related to the durability, yeah, how this concrete when it is exposed to environment and so on, with whether it is degradable or non-degradable, yeah, and so on, yeah, not just considering the initial cost, yeah, but it is good actually because your type of concrete is self-compacting concrete, yeah, so it means that in terms of the construction, it will also reduce the cost, yeah, compared to the normal concrete, yeah, because you use less energy, less people, yeah, to involve in the production and construction. Okay, so I think my time is is running out, yeah. So thank you. I think it's enough from me.
Thank you, Prof. Iwan, for your advice. We will continue the progress in the future for the greater good, sir. Thank you very much.
Okay.
Thank you very much, Professor Stefanus, for the question. This is the end of question and answer session. Thank you very much for Semar Adhideva team. You may leave the Zoom meeting. Thank you.
Thank you all the Stay healthy and stay safe. Goodbye.
Okay, for Mr. Ivan, Prof. Abdul Rahman, and Professor.
The next team who will present is Team Ragex from King Mongkut Institute of Technology, Ladkrabang. Its member consists of Lakshmanat Kodel, Jirayu Intara Parasup, and Chawin Chopani. I'm sorry if there's any mispronounce of the name. I would like to remind you that your time for delivering the presentation is 15 minutes, and it started whenever you start to speak. After that, there will be a 30 minutes interview. So without further ado, for the Ragex team, the screen is yours.
All right.
All right. So good afternoon and hello to auditors and committee members. It's me, myself, Jilayu, and we are team leaders representing KMITL University from Thailand. And we are so glad and honored to join the International Concrete Competition.
Yeah, from what my friends say, we really are. We made it so far to the final. And hi, it's me, Chawin.
And finally, it's me, Leknath Podil. And by giving some praise and honor to the committee members, I would like to start our presentation slide. So here's the basic overview of what our presentation would look like. The first thing is we will consider talking some background of our innovation, and the innovation materials would be the second part. And how do we obtain the materials? How do we get some research idea about it? And also we will discuss about its advantage and disadvantage of it. And finally, we will conclude our presentation with some analysis, and also we will dig deep into LCA and LCC in our final part. So to begin with, as you know, the concrete has been a very major source of attraction in these construction sites in recent time, and it has been since a very long time ago. And the sad thing is the cement, which is a prime factor to contribute towards concrete, produces some harmful gases like carbon dioxide, and that's where we civil engineers need to take more concern. And the first step we are trying to do is preserve our nature, and this is exactly what we are going to do with our innovation in this competition. And for our innovation ideas, we have got up with 3 different materials. That's XL powder and waste concrete stone powder and glass scrap powder. For your information, we have all used these materials by sieving beforehand, so that we only get required amount and also the best product. And for the amount, we have used 225 gram of XL powder, 200 gram of waste concrete stone powder, and 200 grams of the glass scrap powder. And to talk a little bit about XL powder, I would like to introduce my friend first. Mr. First, it's yours now.
Yeah, thank you, Alex. Yeah, from what Alex said, we use XL powder around 225 gram, or it means 0.45%. About 95% of the dry eggshell is calcium carbonate, and it has more calcium content, which will increase the strength to the concrete. Where can we find it? As you guys know, we can find it in your hometown kitchen or unmanaged garbage disposal. As you know, every product also have good part and bad parts. So let's talk in good part first. In the advantage part, eggshell powder also increase the strength of the concrete. Secondly, plasticity index in the soil can be improved by adding eggshell powder. In the disadvantage part, it lost lump workability, and its hydration property drop with age of concrete. Yeah, from the research study, compressive strength is higher than control concrete for 5%. Eggshell powder replacement at every killing day. Eggshell concrete gives greater speed tensile compared to concrete. Without eggshell powder. Move on to this part. My friend Om will talk about it.
Thank you so much first. So in the part of wet concrete stone powder, we are using 200 grams, which is equal to 0.4% of total aggregate in our competition. We'll continue with where we can find those sources. The most highly sought should be construction site and home surrounding. because people throw whatever they want. So we decided to reduce the concrete setting in our laboratory. And wet concrete stone powder also has advantages and disadvantages. And the advantages are environmental conservation and reduce overall porosity and shows improvement in the part of our concrete strength. Disadvantages are its paste might decrease the quality of aggregate and sometimes found to be containing undesirable impurities. And according to the research shows, approximately 85% of the construction waste come from concrete demolition. And I will pass to my friend Alec for the next one.
Thank you very much. Now we have moved to the final part of our materials that we used, and it is sieve glass scrap powder. The ingredients that required to make this scrap powder is that sieve glass, and obtainers of this glass scrap could be obviously from our home surroundings. You know, we being a developing countries, we can see this kind of social issues everywhere near our locality, right? So yeah, it's a very useful way to demolish this problem if we have some innovative ideas. And here's a small video demonstration from the United States, how they do their disposal act and how they contribute it towards industry for manufacturing and recycling process. And here they have used this water bottles from a dumping site, and they have thrown it to the container, and now the final product, or what we say glass scrap, has been ready from the factory. And to make it further useful, we are using the powder itself so that we'll get the best product and quality. And like all other materials, we have some pros and cons of scrap powder as well. The advantage would be that it is very easily accessible everywhere in our locality, and it's actually useful if we can do some recycle. But sadly, there are very less survey results that they have been doing, and that I will talk in the disadvantage part. So we already know that there is something called ASR, alkali silica reaction, that might hamper our aggregate. So in order to reduce this factor, we have used less amount of cement, which will reduce the alkali itself. And according to the research, like I said, it's very useful to recycle, but sadly, just 34% of those waste glass bottles are only recycled due to numerous issues, one being very time consuming and inefficient process. And for taking this slide into further episodes, I would like to introduce my friend first once again.
Yeah, thank you, Alex. Also, we also use admixture, which name it water reducing admixture. We use it around 50 ml, which means 1.25%. It consists of organic and inorganic compounds to reduce the water requirement. Okay, let's talk about advantage and disadvantage. For advantage, it can have a lower water stream ratio. And for disadvantage, the main disadvantage is loss of workability. As you can see from our experiment, we also face with this problem. And move on to this part. My friend Om will talk about it.
Thank you so much. So let's take the main motives behind the innovation, which we all mostly talk about are environmental, easily accessible, economical, and highly influenced by the policy of reduce, reuse, and recycle, and also mitigation of global issues. And lastly, best possible use of wastage. And I would like to pass to Alec for the next one.
Yeah, like our friend said, it's a very useful ways of utilizing those waste products in our locality. And we have come to the discussion part of our complete test result. And here in the screen, you can see all the details of it. For your information, we did some preliminary tasks, including drying and sieve analysis that we did ahead of time before our concrete competition day one. And we did first sieve analysis and then keep it in oven for around 1 day, and it was heated to around the temperature of 100 degrees Celsius, and our to cement ratio was 0.56, which is why we got a shear slump instead of a true slump, which would be actually a very good test requirement in every every concrete structures. And also the ratio of cement, sand, and coarse aggregate, as you can see there, we used 1:1.5:3, which is a standard ratio in Thailand. And the benchmark that we kept for our that we got from our result was 17.23 megapascal. And also there we use two major techniques as our strategic plan. The first thing is we wrapped our concrete after we finished that molding process with plastic, just to not let the air react in between the concrete and the surface. And later on in day 2, we did this thing called capping. As you can see in the figure in the right hand side, that yellow color is the of concrete that we used just before taking the concrete into the testing specimen. And now let's talk a little bit about the life cycle assessment and life cycle cost of our innovation. As you all know, that the recycling operation has like numerous benefits, and among them here are some of the listed benefits, and which is actually very reliable and useful in this modern era, as we are living in, you know, the drastic changing environment where we are facing global issues, global warming, and all these kind of negative impacts into the environment. So it is our duty to preserve our nature by ourselves. So we have used these waste products as our innovation in order to at least help to some extent to better our motherland, or better our mother earth. And here is a flow chart that we obtained. You can see in the left hand side we have all the products, ingredients, cement, Portland, water, and natural aggregates. And the first thing we need to consider is the heating cost. The heating and cooling maintenance cost should be the first priority that we need to consider even before we start any kind of project. And the optimum balance between the initial cost and the future cost that will occur while we are designing the parameters, or designing any sort of concrete structures, should be taken into consideration. And sad part is that even we produce any kind of materials, there will obviously be some greenhouse emission and landfill emission, which is actually a saddening part, but still we can minimize that percentage, and that's what we are doing. And in this one, I want to talk a little bit in depth about response survey methodology, and it was done from the De La Salle University in the year 2017. It's a pretty good chart that you can see here, a 2D picture of what we call response surface. You can see in the picture that the desirability of simultaneously by minimizing the cost as well as increasing the strength of concrete. That's the main idea behind our innovation, right? We want a high early strength concrete with minimal cost, so that it will benefit all other users. So taking that into consideration, here they have designed a model, and it has clearly shown that the percentage of cement replacement that we do, and the percentage of the Excel powder or any other additives that we use for our materials will significantly increase the desirability, and it can fulfill the demand of the consumers as well. And lastly, we have come nearly to our end of the presentation, and we would like to share this motto towards you: we only have one earth.
Why not let's try and preserve it?
Better late than never.
All right, and here's all the references that we took for our presentation making, and it was very wonderful sharing our innovation ideas and materials with you. And that's it from our side. Thank you very much for your attention, and we look forward to question and answer session.
Okay, thank you very much for Ragex team. And now we will enter the interview session. And for this session, we will be divided into 3 sessions, and there will be 10 minutes for each juries. So for the first jury, Professor Dr. Abdurrahman bin Mohsen, the time is yours.
Okay, thank you. What? Ragex Street. Yeah, your team. What is the name?
Yeah, Ragex.
Ragex. Ragex. Okay. Okay. So thank you very much for your presentation. Okay. So before that, do you have any title of your concrete or whatever?
Yeah, it's like preserving the nature with sustainable construction materials.
Oh, okay. All right. Okay, so you are using how many? Three types of material, isn't it? Waste, concrete, stone powder, glass, scrap powder, and also eggshell, isn't it?
Right. Yeah.
Yes.
Okay. In the concrete mix, so what this waste powder being used for? Is a replacement for cement or replacement for aggregate or what?
It is kind of
Replacement for
additives.
cement.
All of them.
No. It's actually minimizing the use of cement, using this as an additives.
Okay, so waste concrete you use as a cement replacement. Waste concrete, Sebelas, scrap powder, and eggshell.
We mix this as an additives.
Additive, so which means that it is additional material.
Yeah.
It is not replacing anything.
Oh.
Yeah.
Why you do that?
It's because, like I said in the presentation slide, that by whenever as we all know that producing cement causes many harmful gases, like carbon dioxide is produced, right? So the main purpose is to preserve our nature, and by taking that into consideration, we have come up with this innovation idea. At least if we can minimize the use of cement in our innovation, then it will be a little bit helpful for other consumers as well as we builders, because the cost of cement is quite volatile, right? And it will be a necessary step for preserving the nature as well. Yeah.
Okay, so how you minimize the use of cement? Your method of minimizing.
Sorry, yes.
How the way you minimize the use of cement? So because you don't replace any part of the cement.
We replaced. We didn't use like almost all. I mean like the cement that we used, water to cement ratio that I showed here, a bit higher, which means that we used less water than the cement.
Now, what is your water cement ratio? 0.5 something, isn't it?
Yeah, 0.56.
So water and cement more or less equal.
Yeah, here 0.56.
Half of the cement. 0.56. It is just normal concrete.
Yeah, 0.4 to 0.6.
Okay, so because your intention is to the use of waste concrete, stone powder, sieve glass, scrap powder, and also eggshell powder. That is for the purpose of what?
For purpose of it's for the purpose of using those raw materials that is already existing in nature. We can see this eggshell powder, waste concrete, stone, and glass scrap everywhere in our surrounding, right? And it has been doing adverse effect rather than good effect. So if we can utilize those products,
how all these ingredients affect the concrete? So meaning to say that if let's say you are not replacing, then you just as if that this concrete being the dumping site for this waste concrete, stone powder, sieve glass, and eggshell powder. So if let's say it doesn't contribute to anything,
it will affect the strength of concrete.
How?
The research has shown that if we use eggshell powder, it will increase the split tensile of the concrete in compared to without using it.
So what is the chemical compound or the chemical compositions of this eggshell powder?
Sorry?
What is the chemical composition?
For eggshell powder? Eggshell powder consists of eggshell powder, calcium carbonate.
Calcium carbonate.
Yeah, so it means
is
that
there any reaction inside the concrete between the calcium carbonate and whatever the ingredient inside the concrete?
actually calcium helps in making the strength of concrete, more amount of calcium.
Is there any reaction? Because this calcium carbonate. So as far as I understand is, if let's say calcium oxide, it's not the calcium carbonate.
You mean for eggshell, right?
Yeah, eggshell.
Eggshell.
That's
Yeah,
why the first question is the first question that I ask you is, what is the purpose of this waste concrete inside the concrete mix? Whether to replace part of the sand, to replace part of the cement. But if let's say as additive, so which means that you are not minimizing the use of cement, the same cement, and then you just add eggshell, add this concrete powder, glass scrap powder. So that's the one that I asked initially lah. Because we need to understand the function or the focus of this new material that we add into the concrete mix. Because the theme is sustainability, high early strength, and quick in construction, isn't it? So those are the theme.
Right.
Okay, all right. So the eggshell powder you just crush, you grind.
Yeah.
Is there any further treatment or
we sieved,
heating or whatever it is, or
we
that you
sieved.
crush?
We
Okay,
did sieve
from this eggshell, and then you crush, and then sieve, and then use inside the concrete.
Yeah, we crush, we grind it and make it into the sieve analysis test. Yeah.
Yeah, make it powder lah.
Yeah.
So which means that you add into the concrete is the calcium carbonate. It is not calcium oxide. So normally when you add calcium carbonate, the reaction, there's no reaction. If let's say you want to increase the strength due to the eggshell, so you need to conduct treatment, especially heating the eggshell powder. This one calcium carbonate convert to become calcium oxide, like the composition of cement.
Yeah, like I said, we did. Yeah.
Okay, you want to say anything? Say. You want to say anything?
Yeah, we did the drying process, like I said. In the drying process, we dried all our ingredients.
Okay, you dry, but at what temperature?
More than 100.
More than 100 is what temperature?
About 110.
110. Okay, that is to release the moisture content only. To change the chemical behavior, from calcium carbonate to calcium oxide, you need to heat the eggshell powder up to 400, 500 degrees Celsius or 600 degrees Celsius. Then the eggshell powder become reactive. If let's say it is not reactive, non-reactive, then it is acting just as a filler only inside the concrete. Similar to waste concrete powder and glass powder.
I see.
Okay, so one day, how many? What is the strength of the one day?
One day, maximum was 17.23 megapascal.
Okay, yeah, strength.
Yeah.
Okay, 17.
Yep.
Okay, all right, okay. All right, so thank you. And my time's also up. Finish time.
Thank you.
Okay, so thank you very much.
Okay, thank you for Professor Dr. Abdurrahman bin Mohsen for the questions. Now we are going to move to the second jury. For Mr. Iwan Supriyanto, the time is yours.
Yes, thank you. Can you hear my voice?
Yeah, we can.
I can hear you.
Okay. Ragex.
Ragex,
You use
yeah.
Ragex. Concrete waste, yeah. Concrete waste from demolished building, right?
Yeah.
It should be
Yeah.
from demolished building because it was already
Yeah.
there in our laboratory.
Yeah. My question is, I'm just wondering that the concrete waste came from some demolished building and various concrete type, concrete grade. Yes. How
Yes.
you answer? How you select? Maybe how you answer that the concrete waste have a different concrete type, concrete grade than you use in your concrete mix. How you answer that? Because this is a concrete paste, right? You know, maybe from source A, B, C has a different concrete grade. Maybe FC 20, 30, 50. Then you mix, then you crush, use as a cost aggregate in concrete. How you answer that this a different
Grade of
concrete type
concrete.
of, yeah.
Actually, we need to look a little bit deep into it. We use the materials that were available in our laboratory, which means that in our lab, I think it was already, pulverized already in our laboratory, and it was there, and we use certain sample of it. And I think they have used the grade which is standard in Thailand. Maybe that should be the grade that they used. And talking about that demolition of buildings and how do we distribute it, or how do we separate it from others, maybe there should be some techniques, but apology from us that we have not read everything, or we have not researched about it in detail, but definitely we would look forward to getting some knowledge about it.
Okay. You use 100% for cost aggregate came from concrete waste or combined with normal cost aggregate?
Yeah, we use normal course aggregate, and we use, as I said, these innovation ideas as an additive. So we use very little amount of them so that it won't affect much to our concrete structure.
Okay. For glass scrap, have you done some? You mentioned about alkali silica reaction,
right?
Can you show the slide in glass scrap? Yeah, you glass scrap. Yeah, yeah. Like it as alkali silica reaction of concrete containing glass. Can you explain what is different properties on in terms of alkali silica reaction between normal concrete and the concrete containing sieve glass scrap powder? Hello?
Alex, your mic is crossed. Mic is off.
Oh yeah, sorry.
Yeah. As we all know that glass is consist of sand, limestone, and other natural stable materials. And when we mixed it with uh, with this concrete, it will have some alkali silica reaction. This is a very likely process that we can see in mixing these ingredients. But the thing is, how do we control this alkali silica reaction is very important to know. And with that, if we would try to lessen the cement ratio and use in place of cement, then that should be a pretty good way to avoid ASR. Because if you consume less amount of cement, then there will be reduction of silica, and there will be less chances or less likelihood of this reaction.
Okay. So you mean by using this material, the alkali silica reaction will be increased compared to normal concrete?
The strength will the strength will definitely increase due to this properties of this glass scrap, the hardening properties, right? Yeah, the hardening properties. Right.
Yes.
So it will definitely increase. Yeah, that's the prime concern, like I have highlighted here. The ASR, if we can figure out how do we reduce this alkali silica reaction in it's okay for us to use it in small scale, right? But then if we are going to use it in large scale, for example, in industry, if we are manufacturing this concrete in large scale, then we need to definitely avoid maybe to, or take some technical decision in order to mix this type of ingredient, I would say. But for now, for the time being, we used it as kind of innovation idea. For actually, we are just using for it a dimension of 15 by 30, right? The concrete cylindrical shape, and it was limited. And just because it was a smaller amount, we thought that it would not make, or it would not hinder much of the performance of concrete, and that's the reason why we use this as our innovation idea.
Okay. Another thing is, I'm also wondering, since using this is came from glass, is there any hazard potential when you mix this material into the concrete? Maybe hurting your hands because very sharp,
right?
Huh?
Right. Yeah, right. So that's why we used it as a powder. We grinded it very small shape. It's like the composition, it's almost similar to cement, and we used as a powder. So in order to avoid that, we used like that. But in this video, you can see from United States that they have produced, this is the final product or the scrap they produce from industry, right? And after this, there are certain steps even after this. That's the grinding process. And we did this in small amount, like for some experiment, we just used small amount, and we hope it contributed positively in our concrete.
Okay, so what is the most chemical content in this glass powder?
Glass scrap,
silica or glass scrap?
It's sand and limestone.
The chemical content properties.
Do you mean
of
like
this
chemical as mixture?
Yes. No. The chemical properties of this material. So you use this one for sand displacement, right?
It is used not actually sand displacement, but it actually we used it in very small amount as an additives.
Okay. So your compressive strength result is around 15, right? 15 MPa.
It was 17 MPa.
Yes. So can you explain what is the most factor contributing on your strength result?
Yeah, it must be that the water cement ratio was 0.56, which is a little bit far right to the actual ideal 0.5 to something around 0.5 would have been a better option for us, but while we mixed, we happened to make it of 0.56, which gave us shear slump. And actually, for a good mix of concrete, actually we need to have true slump, right? But then this shear slump, we still managed to get 17.23 MPa from this shear slump. And yeah, that gave us, most probably it should be water cement ratio.
Okay. Thank you.
Thank you very much.
Okay, thank you very much for Mr. Iwan Supriyanto for the questions. And now we're gonna move to the third jury for Professor Stefanus Adi Kristiawan. The time is yours.
Thank you. Good afternoon, Ragex team. Can you show your make composition?
Yeah. Wait a second. Is this?
Yes. How did you come up with this proportion?
The ratio of cement, sand, and coarse aggregate?
Yes.
It was actually advised from our professor, and also it is the standard ratio here in Thailand.
Oh, for example, if I want to make concrete with other target of strength, yeah, how can I modify this ratio?
The ratio can be modified by the content of, first, I think the most priority should be cement content. And with that, we can modify it.
And is there any procedure how to modify, or just make a trial?
We did pretty much like we did like making a cement as our pivotal, the main one, and then modify other ratio in according to that cement ratio, cement content.
But we actually like test for like different water ratio for like fourth or fifth time. But the highest strength will be like the less water.
So it means he meant to say that it's like a empirical ratio. Yeah.
Okay, so it means that if someone want to make a concrete with different strength, isn't there any guidance or procedure that he can follow so that his target will be achieved?
Right. Very good question. Since we had this obligation in our concrete competition, we were only allowed to use certain amount of cement, right? And we were not allowed to use any kind of other materials like fly ash and other stuff. So taking that into mind, we came up with this idea. But for others who are trying to make concrete in a bit larger amount, maybe the modification should be somewhere near this ratio, or yeah, they need to, I think, modify in somewhere around this ratio. I don't know, I would love to hear what is the ratio there in Indonesia.
Okay, never mind. Because in Indonesia we have a procedure, yeah, that we can use to make a proportion for certain target of strength.
I see.
Okay. In your case that you use this proportion, right? And then you added some other material, three, egg powder and powder, with concrete powder and sieve
Glass
plus scrap. Yeah. Okay.
Yeah.
My question also similar to the previous one. How then you take the amount of this material when you want to use it in your concrete?
This is actually this is actually an idea that came up into our mind, right? We thought like, why not try this method by backing with the research fact and every evidence that we have already shown in our presentation session. And the amount, I think we are not that professional enough in order to give the prescription or the amount details in that would be beneficial to use in factory level. So I guess this was our effort to get some higher strength by using in community level or very small level. So for us to go into factory level and large scale, I think definitely we are not mature enough for that.
Okay. Maybe the previous judge already note that since the preparation to make this material is purely mechanical, yeah, just crushing, grinding, and so on, so that you obtain a powder form, yeah. So it means that this material is not reactive, yeah. It will be inert. So when you put this material into concrete, it will act as a filler more rather than the cementitious material, yeah. So in this case, do you think that how do you think that this material can somehow improve the strength of your concrete?
We did some research and we find that all of these materials to some extent push the boundary of strengthening the concrete, like we have talked about in every slide. The research has shown that it will somehow increase the strength of materials, and that's the thing we consider.
Okay. The next question is,
for example, this one. They have said that if we use Excel powder, but the thing, Excel powder drop its properties with a concrete, which means that it will only be useful in lesser amount. That's actually what we need, a higher strength, right? So we need strength in earlier days, and that's the reason why we chose this material.
Okay. Also, do you think that the use of this material will have will affect the workability of your concrete?
Definitely, the workability is also a concern that we need to focus on while we are designing or while we are constructing any kind of structural, be it like small structures like we are doing concrete structures, any stuff that we civil engineers normally do. And the workability is the prime factor that we need to consider if we are using these kind of ingredients. And the research and the studies that we did throughout this competition shows that it will somehow increase the workability. But the thing is, this some of the ingredients that will take time in order to show the performance of their workability in the concrete. And actually that's the concern that we need to consider. Yeah.
It is increasing or decreasing the workability?
Workability, if we look at a long run, it would gradually increase, but for short time it's nearly to not significant. Yeah.
Okay, thank you. I think my time is running up. Only 20 seconds left, so I think finish from me, and I send back to the committee.
Thank you, sir.
Thank you.
Okay, thank you very much for Professor Stefanos for the questions. And this is the end of the interview sessions. Thank you very much for Ragex team. You may leave the Zoom meeting room. Thank you.
Thank you very much. It was a pleasure joining the competition. And everyone have a good day.
Thank you. Have a good day.
Good afternoon. The last team who will present today is Abidin Ganesha from Tunas Pembangunan University, consists of Chandra Tumowo, Afi Alfian Ubaid Khairi, and Sabar University. It would like to remind you that your time for delivering the presentation is 15 minutes, and it started whenever you start to speak. After that, there will be 30 minutes in the field. Okay, for the Abidin Ganesha team, the screen is yours.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen, and especially to the other judge of Civilweek of International Congress Competition Civilweek UNS 2021 with sustainable high strength concrete for use constructions. Sebelas Maret University of Surakarta.
And we are Abidin Ganesha from Tunas Pembangunan Surakarta University, Indonesia. My name is Afi Alfian.
My name is Chandra Tumowo.
My name is Sabar Sidik. Today we are ready to presentation with our innovation, and the title is Innovation Sustainable of Green Concrete with High Early Strength Self-Company Concrete using Brick Waste Powder and Concrete Waste Powder.
And the next is background. Nowadays, construction field is growing very fast in the process of producing cement. Also, products much of carbon dioxide, which play a vital role to global warming that happens in this world. And self-company concrete is one of the great innovation that happens in this opportunity. And where this concrete has a high workability, but also don't neglect the compressive strength. Therefore, a sustainable material is brick waste powder and concrete waste powder.
And the next is Self-committing concrete. Self-committing concrete is a concrete that can compact without any suffocation in the concrete, based on Akumara and Oshii 2003. There is 3 methods to make self-committing concrete. The method is 1. Minimum of VC feeder, 2. Limiting quantity of aggregate, 3. Additive application. And the characteristic of self-committing concrete is filling ability, passing ability, and suffocation resistance. Next.
And the next is sustainable green concrete. Green concrete is the type of concrete that resembles conventional concrete, but the production or use of the concrete requires a minimal amount of energy and does not cause harm to the environment as well as recycled aggregates material, reducing the additional burden on landfill and reducing aggregate wastage. Green concrete can be considered an element of sustainable development because it is environmentally friendly and is widely used in the green building practice.
And the next is brick with powder. The main advantage of using brick with powder is to replace cement, which also reduces pollution from cement productions and bricks disposal, based on K. and Zhang 2012. Brick with powder can be classified as a pozzolanic material because the sums of silica dioxide, aluminum tetrioxide, and ferric tetrioxide is more than 70%. And we can look together. This is chemical compositions of brick with powder. Shorts, Pedioco 2018. The silica dioxide is the highest compositions in 67.35%. And the percentage using brick with powder, the highest portion is 10%.
And the next is concrete with powder. Concrete with powders is a byproduct in the production of recycled concrete aggregates, an isolator that is intended for cement hydration. It can increase the compressive strength of concrete, based on Wang, Yao, and Stephen 2019. And we can look together the chemical composition of concrete with powder, sourced by Mediana et al. 2014. We can look together the silica dioxide is the largest, the composition is 51.8%. And the percentage of using concrete with powder, we get the position in 10%. Next.
And the next is coarse aggregate. Coarse aggregate that often used in the concrete mixture are gravel and crushed stone. Coarse aggregates are the particles retained on 4.75 millimeter sieve. The quality of coarse aggregate can be measured with Los Angeles abrasion test, where the result must not be more than 50% of initial weight. Locally available coarse aggregate from Klaten was used with specific gravity of 2.65. The requirement of coarse aggregate for concrete mixture are 1. Coarse aggregate may not contain more than 1% clay against dry weight. 2. Coarse aggregates come from sharp and hard particles, impermeable and cubically shaped.
And the next is fine aggregate. Fine aggregate are often referred to sand. Fine aggregate work as a filler which differs from natural sand. Based on EN 12620, the requirements of fine aggregate for concrete mixture are 1. Fine aggregate might not contain more than 5% clay. 2. The sand particle used in concrete mixture must be sharp, hard, and parental. 3. The sand storage must be separate from the other material.
And the next is Consol P102HA. Consol P102HA is a unique, versatile super fertilizer that is perfect suited for precast concrete production. In addition, it provides very high water reduction, high initial strength, and excellent flow characteristic. The Consol P102HA is for 1. Wide variety of application requiring good initial strength development. 2. Concrete with self-committing concrete water reduction up to 30%, and the highest performance concretes.
And the next is election material. You can look together. Cement, 3 roda OPC cement, super plasticizer, Consol P102HA, concrete with powder, brick with powder, fine aggregate, coarse aggregate.
And the next is mix design. Mix design using ACI 211.1 methods. We can look together. This is mix design final from Abidin's Ganesha team.
And a blending slump flow test from fresh concrete based on standard EN 12350-8-2010 with planning 3 samples of concrete by Abidin Ganesha to target to compressive strengths on one day is 32.07, 32.31 MPa, and 32.55 MPa.
And the next is slump flow test of fresh concrete based on standard EN 12350-8-2010 with blending 3 samples of concrete which were tested at UTP Surakarta Concrete in October 12, 2020. We have compressive strength 1, 32.47 MPa, 2, 31.31 MPa, 3, 33.01 MPa. And we have average 3 sample concrete is 32.26 MPa.
And the next is the analyze aspect of environment, aspect economy, and aspect social. Aspect of environment. 1. Reduce the environmental pollution. 2. Reduce the waste productions in environment. 3. Reduce the global warming, because we know that cement is the largest contributor to carbon dioxide gas in the world. 4. Use of waste material and reduce the effect that disturb health or safety on construction user. Aspect economic. 1. Increase the income of business sector, such as brickmaker and worker constructions. 2. Can reduce budget costs on self-competing concrete planning, because our concrete use lots of cement. 3. Can save costs up to 300,000 rupiah per meter cubic than normal concrete. An aspect social. 1. Will be more time efficient. For example, in roads constructions, usually takes 20 x-day can be 1 day to do for ACC concrete process. 2. With fast constructions, it will make infrastructure easier to work on.
And the next is concrete cost budget plan from Abidin Ganesha is a 1,600,000 rupiah, and the cost budget on normal concrete is 1,900,000 rupiah, and can save is 300,000 rupiah.
And the next is LCA, or Lifecycle assessment. Lifecycle assessment is a cradle to grave-based method, analysis of the entire cycle from production process to waste treatment, which is used to determine the amount of energy, cost, and environmental impacts caused by the stages of product life cycle, start from the time of taking raw material until the product is finished being used by consumers. This step is an alternative one, with the level of detail effort depending on the research objective. The steps are: 1. Defining objective and scope. 2. Inventory analyze. 3. Impact analyze or assessment. And 4. Interpretation.
And the last is Lifecycle cost. Lifecycle cost plan is a plan regarding the issues of proposal for a construction project throughout the life on the project. In the implementations of development, starting for idea, feasibility studies, planning, implementation, to maintenance and demolitions operations require various costs, which are grouped into several components, namely A. Initial cost, B. Maintenance. The initial cost for our team of Abidin Ganesha teams, we can look together the subtotal 7,800,000 rupiah. And the next is maintenance for Abidin Ganesha teams. The total is 4,008,000 rupiah.
And the next is conclusion this presentation. 1. Based on the research that has been done, brick waste powder and concrete waste powder are used as cement substitutes. 2. The use of the large quantities reduces cement production, thereby reducing greenhouse gas generated from cement production. 3. By using concrete waste powder and brick waste powder will save time, be economical and environmentally friendly. 4. This innovative concrete using brick waste powder and concrete waste powder save manufacturing cost of EDR 300,000 rupiah. And 5. Based on BSEN 1971, which require the concrete to have compressive strength of 32.36 MPa at 1 day, whereas the concrete, which using this innovation, achieves strength of 32.26 MPa at 1 day. Besides, the usage of concrete waste powder and brick waste powder could save the cost needed to make a high aerial strength of competing concrete.
And the next is suggestion for our team. There's need to deeper research and support from various practice regarding the use of the concrete waste powder and brick waste powder used as cement substitute, so that it can be recycled for something full of 32.36 MPa or K388. The comprehensive test of our concrete innovation at 24 hours. Next.
And the next is application projections from innovation sustainable of green concrete with high early strength, self-competing concretes using brick waste powder and concrete waste powder for structure, column, block, roots, and very tall building. And our team just want to say thank you. And the next is session question and answer. The times will back to the Comets Achieve Civilweek International Competition 2021. Thank you.
Thank you very much for Abidin Ganesha team. For question and answer session, there will be 10 minutes for every jury. The first, Professor Abdul Rahman. The time is yours.
Okay, so thank you very much. Thank you, Group Abidin Ganesha. Thank you for your presentation. A very energetic presentation, I would say. Okay, so your title is what? Innovation, innovative. The title, your concrete. Can you show the slide? Okay, can you show your slide?
Okay, wait.
Okay, okay.
Your title.
Your title, okay.
I think number 3.
Number 3. Yes, of course, yeah.
And innovation, sustainable, green concrete with high early strength, self-compacting concrete, using brick powder and concrete waste powder.
Yes, that's right.
Okay, so you have early strength and also self-compacting. Yeah, okay.
Yeah.
Right. So based on the sustainability, on the respect of sustainability, can you explain from your title how it what that reflects to the sustainability of the concrete? Based on your title, this one. Which one that reflect to the sustainability?
Okay. Sustainability is one of the purpose for our teams about the concept. Because new sustainable is one of the solutions currently to stop using cement back to our concept today. Because our innovation we will try to reduce the cement and can be upending our innovation. And using concrete waste powder and brick waste powder is one of the purpose on our team to share positive value and can be knowledge and information for many people. then sustainable green concrete can be applied is one of the solution about issue. Thank you.
Okay, all right. So you are using, meaning to say that the waste product, brick waste powder and concrete waste powder, yeah, because waste powder that relate to the sustainability. Yeah, okay, all right. Okay, in your mix, in your mix design, you use brick waste powder and also concrete waste powder as cement replacement. As cement replacement material.
Yeah.
Yeah, okay. So brick waste powder 10%, concrete waste powder 10%, replacing cement.
Yes.
Yes, of course.
Okay, okay,
Yes.
all right. So the brick, what is the compound composition or chemical composition of the brick that enable the brick waste powder to be used as cement replacement material? The brick. What is the chemical composition?
Okay. Thank you for this question. So, what the composition of chemical of the brick waste powder? In brick waste powder, it have also many chemical. Some like silica dioxide, aluminum dioxide, and ferro dioxide. Yes, and we can call that chemical is the pozzolan. Yes, because the pozzolan is a material that contain silica compound or silica alumina, do not have a cementitious binding properties, but are smooth in the percentage water with the water. The compound will reaction with the calcium hydroxide at normal temperature from calcium hydrate.
Okay, all right. Can you show the chemical composition of this brick waste powder? I think what slide? Slide number one. Chemical composition, the chemical, silica, alumina, and so on.
Yeah, silica, alumina.
Your chemical composition of this brick waste powder.
The next slide. No. Back to Zoom.
Is that? I think you have.
Slide.
Yes. Share. Yes.
Chemical composition.
Next.
Brick waste powder and what? Silica.
Yeah.
Silica more than 70%.
Yes. Yeah. This is the chemical compositions of a brick waste powder.
This one. Okay. All right. 67%.
Yes.
Is the silica reactive or non-reactive silica? Do you do any test? Pozzolanic reactivity, the one that you said that brick is a pozzolan material.
For our team, prefer to choice innovation today based on the test and in the proposal in the attachment. We can look together based on the test on Sebelas Maret University Faculty of Science and Mathematics, and based on the test, these materials can be called a pozzolan, which is like based on Petrioco and 2018 journal. This can be solution and can be called the next pozzolanic material.
Because it depends on the reactivity. If let's say sand, just normal sand, it also contains silica, but it is not reactive. So something that you want to replace cement content, so that material must be reactive. Same thing with brick waste concrete waste powder. So concrete waste powder, it contains also aggregate inside, isn't it? Coarse aggregate and fine aggregate. Am I right? Or you separate? Concrete waste powder. You have a concrete and then you crush, isn't it? become powder.
Yes.
Yes, that's right.
Okay, so the same thing, the same question. Okay, is the silica inside the concrete waste powder reactive or not? If let's say it is not reactive, but because when pozzolanic material, so we need to test this reactivity. We call that as pozzolanic activity index. If let's say it doesn't react, then it's just acting as a filler only lah. Because the crushed concrete waste powder means inside there is a combination of cement, sand, coarse aggregate, isn't it? And then you crush, become fine powder. Am I right?
Yes, right.
So coarse aggregate, if let's say you crush, become very fine, will that has any reactivity inside the concrete? Coarse aggregate, you crush into fine powder, can be used as a cement replacement material. Can or cannot?
Okay, for our innovations concrete waste powder, as why not to be substitution for fine aggregate or coarse aggregate? Okay, based on the research come from the test, concrete waste powder is good quality to be substitute cemented use material. Okay, I think it's because on the action reactions, the chemical composition is modern, which is like a cemented and cement, and we will try to using today as a cemented use material because concrete waste powder with mixed designs and collaborations with perfectly using type F, the superplasticizer, especially from the concept we went to HH today, we can have a conclusion concrete waste powders. It can be solutions to make a cemented use. This is our team choice as a cemented use.
So you use superplasticizer to produce the self-compacting, to improve the workability. Okay, it is not related to hydration of cement. Okay, so hydration of cement, when we talk about pozzolan material, pozzolanic reactivity, so the silica must be reactive. It is not something that silica, it is not all the waste material can be used as cement replacement material, although inside the material it contains silica. But the silica is not reactive. Yes, sir. So, I think my time is up. Okay, so thank you very much.
Okay, thank you. Thank you very much. So beautiful information. Thank you.
Okay.
Thank you very much, Professor Abdul Rahman. We're moving to second session. Mr. Iwan, the time is yours.
Okay. Hello, Abidin, Ganesha.
Hello, Mr. Iwan.
Yeah, I have some question. I think the most of question already asked by Prof. Abdul Rahman. But since you use brick waste, what is the major chemical content? The major chemical content is silica, right?
Yes, silica.
Yes, we can look together. This is a chemical. Okay, on the slide.
Silica is the first or secondary reaction in the concrete. Silica dioxide is the first or second reaction in the concrete mix.
Okay, the silica dioxide is the first component, the highest contents.
No,
in the
I mean the chemical reaction. In terms of chemical reaction, if you use brick waste, that's the major content is silica.
Sorry, yes.
Yes.
The brick waste powder is silica dioxide.
Yeah, silica.
Hello?
Yeah, silica.
Yeah.
Right.
Yeah, silica, right?
Yeah.
Right.
So I'm asking you, silica is the first or second reaction in the concrete mix? during the chemical reaction?
Yeah, number
First or
first. Yeah,
second?
first.
Number one.
First.
Number one. Yeah.
The first reaction.
Yeah.
Yes.
Are you sure?
Yeah.
Okay. Calcium oxide and silica. Which one
Yeah.
the first one? The first will be the first reaction in the concrete between calcium and silica.
Silica is number one, and calcium dioxide is number two.
Okay, silica will react with what? Directly with water? Can we directly react with water during the mixing? Silica?
Yes. Silica, yeah, of course. Using the silica dioxide is perfectly when you put the mixture, because effective using perfect come from the super plasticizer type F, because can be unfair why or not the silica dioxide can be perfectly in the mixture.
Okay, silica dioxide, you mean like can be directly react with the water, becoming what? Calcium silicate hydride, or it react with calcium hydroxide that producing during a reaction between water and calcium oxide.
Yeah.
So why I am asking you about this one? Because your 1 day strength result is very high. Yeah? Your 1 day strength. So I just want to know what is the most contribution factor in your 1 day strength, because you only using this supplementary cementing material and should be secondary reaction instead of the first reaction. But in 1 day strength, we need the material that can be react directly to producing the high strength. That means you cannot expect that you can achieve the early strength by using this kind of material. So can you explain how you get the very high strength in 1 day by using this mixed proportion?
Okay, I will
Because
answer.
of what factor contributing on that?
Okay, thank you for your question, sir. The first thing is that we use cement type 1 OPC material, then good quality material based on the test result, and then added with innovation as a substitute for binders that have action reaction that can increase the quality of concrete, and with the use of minimum water to cement ratio and use optimal super plasticizer, and our recent get high early strength based on trial. Thank you.
Okay, and I will adding the answer. All material based on the test, and we will try to using based on good quality. And currently, the support come from our innovations is perfectly, which is like a cement. And supplementary cement is material come from our team. This is our region's choice material, good quality, and water to cement ratio, and using our super plasticizer. Yeah, this is my answer. Thank you.
And I will adding my friend's answer. We must be remember because this super plasticizer for our team is can reduce the water up to 30%. That's why.
Yes, right.
Yes.
Can you show your mixed proportion, your slide?
Yes.
slide of make design, the make proportion. Can you
Yes.
show
This.
one?
This one.
Okay. I have another question. For 1 day strength,
Yeah.
which one have most contribution between cement paste and the aggregate? Which one that have most contributing in the 1 day strike? Cement paste or
Yes.
the aggregate?
For the highest contributor today come from the.
We talk about 1 day strength, yeah.
Yeah, 1 day strength come from the aggregate, and and secondly, support come from
instead of cement.
Yeah, the second support come from the using cement, and come from the table, come from the water, super plasticizer, our innovation, and the big season giving the result.
Okay, my internet is unstable. Okay.
Okay.
So why your water is 90? I mean, your 1 day strength.
Yeah.
Is if you ask the strength, especially in 1 day, is coming from calcium silicate hydrate.
CSA.
Yeah. But your cement content is, I think, it's quite low, and you cannot expect from brick powder to get another calcium silicate hydrate, because this is your second reaction, right?
Yeah.
So that's why I'm asking you, what is the most contributing factor? Is because your strength is very high, 30 MPa, yeah? More than 30,
yeah.
Because of low water cement ratio or because of super plasticizer?
Yeah.
This is polycarboxylate, right? This is polycarb PCA.
Yep, of course. Yes.
Based
Ether. Yeah,
polycarboxylate, right?
Yeah.
Yeah. Okay.
Okay, I will answer. The our mixed design, the biggest contributor come from the best quality coarse aggregate and fine aggregate. Because all the tests come from the fine modulus, specific gravity, and to using how to percent using, and as you know, using fine aggregate is 52%, and coarse aggregate is 48%, and continually support from the cement. After from the cement, we must remember our innovation. Our innovation can be called a cementitious material, supplementary cementitious material, and right. I think the plasticizer console P102HA to reduce water up to 30%, and 30%. I think it can be reduce water perfectly. Yes, perfectly water. And after that, we can look to in the slump flow test. The slump flow test is, I think it's on the F notch is come from our slump flow test. It can be continue this solution. Right. Thank you.
Okay. Thank you, Abidin.
Yeah.
Ganesha.
Thank you, Mr.
My time is up.
Yes.
Yeah.
That's good.
Thank you very much.
Thank you.
Thank you very much, Mr.
Okay, I guess, and this is my turn. Okay.
Okay, hello, Mr.
So I would like to discuss about the sustainability aspect of your concrete.
Yes.
Okay, can you show your slide that showing the sustainability of this concrete?
Yeah. Sustainable green concrete. This right. Yeah.
Not this one. The at the end of your presentation, I think.
Yeah.
Oh,
This is just a definition of the sustainability, but what I would like to discuss is how you quantify the sustainability of your concrete. So
okay, sir. I will answer that question. Okay. How to the sustainable upgrade our team to the future? Yes. Maybe our innovation just the waste. It can be found in all around the world. And from our data and from the internet and other research from our material from sustainable is maybe it had to benefit a lot. But on standard building infrastructure, high innovation, right? Our innovation can continue to be solution to make high strength concrete. So that our team choose the right solution in infrastructure with the further research, and it can be applied the structure from the maybe to column to vertical building.
Okay, sir. I will adding the answer. Why I chose a sustainable green concrete? We must remember about the issue in the world is a climate. Sustainable development goal is one of the purpose for a leader in all one of the world, and we will try to show our potential come from the Congress. We will try to show information and knowledge about a sustainable green concrete today based on our material. Yes, green concrete come from the concrete powder and brick powder. I think it's one of the solutions about the issue at the world, because our innovation is one of the cement it use as a binder our innovation, and we have a conclusion. Big hope the data come from the big powder and concrete powder. One of the solutions about the issue, and we can call them sustainable green concrete. Thank you.
And I will adding again, and we can look together on the present tense. Based on data, concrete with powders around the world. Every country has a lot of this with production every year. This from data from our team. In the 83% for concrete with powder, and brick with powder is 67%. So maybe from the sustainable to the future is not too hard to find this material, and maybe can to be the solution. I think enough.
Okay, I will add it. Why our team chose? Because sustainable green concrete is a revolutionary topic in the history of the concrete industry. It was first discovered in Denmark in 1998. It is a concept of environmental thinking into concrete that considering every aspect from raw material to manufacturing methods, offer mixed design, the structural design, construction, and lifespan. And we tried to research using concrete waste powder and brick waste powder as green concrete because there is not combustion combustion process and by utilizing waste that is not used to make environmentally friendly concrete. Thank you.
Actually, my question is about how you assess the sustainability of your concrete. What method that you use to assess the sustainability?
Okay. The methods for our team choice is come from SMART. SMART is S, specific, M, measurable, A, accessible, realistic, and tempered.
Excuse me to interrupt. Can you go back to the previous slide before this slide? No.
Sustainable.
Sustainable.
Yeah.
Okay.
Sustainable green concrete.
No. Stop. Yes, this one. Okay.
Yeah. Okay. Maintenance.
No. Go back.
Recycle plus.
Or recycle nomor piro?
Previous slide. Before this one. Life cycle assessment.
Yes, life cycle assessment. Life cycle assessment in this.
Okay.
Yes, this one. You in this case you write that the step in the life cycle assessment is defining the objective and scope, inventory analysis, and so on and so on. But I cannot see how you make the objective of your life cycle assessment, the boundary, and also how you make inventory analysis of your concrete.
Okay, I will answer. About innovation, our research impact of LCA is 1. Cradle to grave includes material and energy production, chain all process from raw material extraction through production, transportation and use stage to the final product in its life cycle. And 2, cradle to get includes all process from the extraction of raw materials.
No. So in your case, you quantify the life cycle assessment. The scope is a cradle to get or cradle to grave. For in your case,
cradle to get.
Yes. Okay. This is from the raw material until production of concrete, or from raw material until completing the construction. Which gate do you choose?
Okay, our team choice come from the extractions raw material and truck production stage.
Okay, the
process
of
within
the
factory. Yeah,
okay.
Right.
So, do you have the result of the inventory analysis?
The factory analysis come from, especially come from productions of brick. I'm stay in a Karanganyar regency. The Karanganyar regency is one of the regency come from the biggest and the productions of brick. And I think that's why.
Do you understand what does it mean by inventory analysis?
Inventory analysis. Yeah.
What? So show me the result of your inventory analysis. How much is CO2 emission of your concrete and so on?
Sorry.
It's okay.
Okay. Okay.
Okay. Sorry, because my time is up, so that it's no problem if we have not finishing this discussion. It's no problem. So I will give it to the committee to take the session.
Thank you very much, Professor Stefanus. And this is the end of the interview session. Thank you very much for all the questions for all the juries. And thank you very much for Abidin Ganesha.
Yeah.
Yes.
Yes.
Thank you very much.
You may leave the meeting room. Thank you very much.
Thank you very much.
Thank you for everyone.
Our team just want to say thank you for this opportunity, and our team Ganesha to say see you later and ready.
Thank you very much.
Yeah. Might be enough. Can I leave this presentation? Or
yeah, you may
comment?
leave the meeting room.
Okay.
Okay. Thank you.
Thank you.
Okay, we already reached an end for today's final round, and we will close today's meeting. That is all for today. I'm Devita Putri Maharani, and
I'm Stephen Wijayasamuel.
on behalf of all the committee, we apologize for all the mistakes we encountered from the beginning. That is all from us. Thank you for participating on final round today. Once again, thank you very much. Don't forget to join us on the next day of final round of International Concrete Competition, Civilweek 2021. You may leave this meeting room and have a nice day. Thank you.
Okay,
Thank
thank
you.
you.
Thank you
See
very
you
much.
tomorrow.